They are tiny, they are crimson, and there are thousands of them scattered across the ancient sky like bloodstains on glass. Astronomers call them the little red dots, and the more we study them, the less sense they make. When the James Webb Space Telescope opened its eye on the universe in the summer of 2022, scientists expected to see something extraordinary. They got it, but not in the way anyone predicted. Deep field after deep field came back dotted with objects that should not be there. Faint red specks, each one no wider than 500 light-years across, shining from epochs so distant that even the nearest ones were seen as they existed 12 billion years ago. Barely 2 billion years after the Big Bang. An era when the universe was still assembling its first real structures, still figuring out how to light itself up. And yet there they were, thousands of them. Compact, red, silent in most wavelengths, almost invisible to every instrument we had ever pointed at the sky before Webb. At first, no one knew what they were. Astronomers floated galaxies, failed stars, optical artifacts, noise in the data. Then Webb's spectrograph peeled them open. What it found inside was not a galaxy at all. It was a black hole, not just any black hole, a supermassive one, actively feeding, wrapped in a thick veil of gas and dust, growing at a rate that traditional formation models cannot explain. And it was not alone. Survey after survey confirmed it. The little red dots are not rare anomalies. They are a population. A missing chapter in the story of how the universe built its largest monsters. And if the most radical theory is correct, they did not grow slowly from dead stars. They collapsed into existence all at once, fully formed, in the cosmic dark. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. There are two ways to see the universe. The first is with your eyes. You step outside on a clear night, tilt your head back, and watch the stars do what they've always done. They twinkle, they form constellations. They stay where your ancestors put them in stories told around fires thousands of years ago. That version of the universe is comfortable. It fits inside your head. It doesn't ask much of you except maybe a sense of wonder and the occasional wish on a falling star. The second way is with a mirror made of gold, sitting 1.5 million kilometers from Earth, staring into the dark with instruments so sensitive they could detect the heat signature of a bumblebee at the distance of the moon. That version of the universe is not comfortable. It doesn't fit inside your head. And it asks everything of you, including the willingness to accept that most of what you thought you understood about the cosmos might be incomplete, outdated, or just flat wrong. The James Webb Space Telescope launched on Christmas Day 2021, and by the summer of 2022, it had already started breaking things, not physically. The telescope itself works beautifully, almost suspiciously well for something that had to unfold itself in space like the world's most expensive origami project. What it broke was consensus. What it shattered was the neat, careful story astronomers had been telling for decades about how the universe grew up. And the strangest part is that nobody saw it coming. The telescope did exactly what it was designed to do. It just turned out that what the early universe actually looked like and what we predicted it should look like were two very different pictures. Webb was built to answer old questions. How did the first galaxies form? When did the first stars ignite? What did the universe look like in its infancy, back when hydrogen was still the only game in town and chemistry as we know it had barely started? These weren't new mysteries. Astronomers had been chasing them for decades with Hubble, with ground-based observatories, with every trick and technique available to modern astrophysics. But there was a wall, a limit to how far back Hubble could see, not because it wasn't good enough, but because the light it was designed to capture simply stopped being visible after a certain point. Light from the very early universe doesn't arrive here looking the way it did when it left. The expansion of space itself stretches every photon that crosses it, pulling wavelengths longer and longer the further they travel. Ultraviolet light becomes visible light becomes infrared. And if the light has been traveling for more than 13 billion years, by the time it reaches us, it's been stretched so far into the infrared that a telescope like Hubble, which was optimized for visible and ultraviolet wavelengths, simply can't see it anymore. It's not that the light isn't there, it's that Hubble is looking in the wrong color. Webb was built to look in the right color. Its primary mirror is 6.5 meters across, more than 2.5 times the diameter of Hubble's, and it's coated in a microscopically thin layer of gold because gold is nearly perfect at reflecting infrared light. The telescope doesn't orbit Earth. It sits at a gravitationally stable point called Lagrange 2, a spot in space where the gravity of the Earth and the Sun balance out just enough that an object placed there will stay put with minimal fuel. From that perch, shielded from the sun's heat by a 5-layer sun shield the size of a tennis court, Webb can cool its instruments down to just a few degrees above absolute zero. That matters because infrared detectors have to be cold. If they're warm, they glow with their own heat and drown out the faint signals they're trying to detect. Webb's instruments run colder than the cosmic microwave background, colder than the average temperature of empty space, colder than anything has a right to be while still functioning. 4 main instruments do the heavy lifting. NIRCam, the near-infrared camera, is Webb's primary imager. It sees wavelengths from about 0.6 microns, right at the edge of what human eyes can detect, out to 5 microns, deep into the infrared. When you see those stunning full-color images of distant galaxies that started flooding the internet in mid-2022, you're looking at NIRCam's work. MIRI, the mid-infrared instrument, pushes even further, covering wavelengths from 5 microns out to 28 microns. That's the realm where the most distant, most redshifted objects finally show up, objects Hubble couldn't touch. NENSPIC is the spectrograph, designed to split incoming light into its component wavelengths so scientists can read the chemical fingerprints of distant stars, galaxies and gas clouds. And FGS NIRIS, the fine guidance sensor and near-infrared imager and slitless spectrograph, does double duty. It keeps the telescope locked on target with precision measured in milliarseconds, and it can take spectra of multiple objects at once without needing to physically point a slit at each one. Together, these 4 instruments give Webb the ability to not just see the early universe, but to study it in detail, to measure distances, compositions, temperatures, velocities, to turn dots of light into data. The concept that makes all of this possible is redshift. It's one of those ideas that sounds simple until you try to explain it, and then it reveals layers. When an object in space is moving away from you, the light it emits gets stretched, the waves get longer. If you're watching a star or a galaxy recede, its light shifts toward the red end of the spectrum. That's the Doppler effect applied to light. The same reason a siren sounds lower in pitch as an ambulance drives away. But in cosmology, redshift means something deeper. It's not just that galaxies are moving through space. It's that space itself is expanding, and the light traveling through that expanding space gets stretched along with it. The further a galaxy is, the more space its light has crossed, and the more that light has been stretched. Measure the redshift, and you've measured the distance, not in kilometers but in time. A galaxy at redshift 1 is being seen as it existed roughly 7.5 billion years ago. A galaxy at redshift 6 takes you back to when the universe was less than 1 billion years old. Redshift 10 or higher, and you're looking at the first few 100 million years after the Big Bang, an era when the cosmos was still largely dark, still warming up, still figuring out how to build stars. Webb was designed to reach redshifts Hubble couldn't, and on July 12, 2022, NASA released the first full-color image from the telescope. It was a deep field, a long exposure pointed at a single patch of sky, and the target was a galaxy cluster called SMACS 0723. The cluster itself isn't especially distant by cosmological standards. We're seeing it as it existed about 4.5 billion years ago, roughly the same age as Earth. But that's not why it was chosen. Galaxy clusters are useful because they're massive, and massive objects bend space. Einstein's general relativity predicts that gravity doesn't just pull on matter, it warps the fabric of space-time itself, and light traveling through that warped space follows the curves. When light from a very distant galaxy passes near a massive foreground cluster, the cluster's gravity bends the light's path, magnifying and distorting the background galaxy the way a lens magnifies an image. Astronomers call this gravitational lensing, and it's one of the most powerful tools available for studying the distant universe. Point a telescope at a lensing cluster, and you get a natural magnifying glass for free, boosting the brightness of objects that would otherwise be too faint to see. SMACS 0723 is a strong lens, and Webb pointed at it for 12.5 hours. That's all, 12.5 hours of total exposure time. For comparison, Hubble's deepest images, the ones that defined what the distant universe looked like for more than a decade, required weeks of observation time. Webb pulled comparable depth in half a day. The image that came back showed thousands of galaxies, not dozens, not hundreds, thousands. Every patch of darkness between the bright foreground galaxies was filled with tiny smudges of light, each one a galaxy billions of light years away. Some of them magnified by the lens, some sitting far beyond the cluster in the deep background. The faintest objects in the frame were so dim that their light had been traveling for more than 13 billion years before it reached Webb's mirror. We were seeing them as they existed just a few 100 million years after the Big Bang, in an era when the universe itself was still a child. The image was stunning. It was also expected. Scientists knew Webb would see deeper than Hubble. That's what it was built to do. What they didn't fully anticipate was how much more there would be to see. The density of galaxies at high redshift, the sheer number of faint infrared sources scattered across every deep field Webb observed, was higher than many models predicted. The early universe was busier than it was supposed to be, more crowded, more active, and buried inside that crowd were objects that didn't fit any category astronomers had prepared for. The scientific questions Webb was supposed to answer were clear from the start. How did galaxies form? Not in the abstract, but mechanically. What physical processes took clouds of primordial hydrogen and helium and turned them into the structured, star-filled systems we see today? When did the first stars light up, and what did they look like? Theory suggested they were massive, blue, short-lived giants that burned out in just a few million years, but no one had ever seen one. Population 3 stars, they're called, and they remain entirely theoretical. Webb was supposed to find them, or at least find the galaxies they lived in. How did supermassive black holes form? Every large galaxy in the modern universe has one sitting at its center, some weighing billions of times the mass of the Sun, but the process that creates them is still unclear. Do they grow slowly from the collapsed cores of the first massive stars, or did they form some other way, skipping steps, collapsing directly from giant clouds of gas into black holes weighing hundreds of thousands of solar masses right out of the gate. And how did those black holes and their galaxies grow together? Did the black hole form first and pull in gas that eventually became stars? Or did the galaxy form first and the black hole grow later, fed by gas funneled inward by the galaxy's gravity? These were not idle questions. They shaped the entire timeline of cosmic history. Get the formation process wrong, and everything downstream shifts. The age at which galaxies matured, the rate at which stars formed, the abundance of heavy elements, the conditions that eventually allowed planets and chemistry and biology to emerge, all of it hinges on getting the early universe right. And for decades, the Standard Model had done a decent job of that. Simulations matched observations, predictions held, the story hung together. Then Webb turned on. The first hint that something was off came almost immediately. Within weeks of the telescope's first science observations, astronomers started noticing objects in the data that looked wrong. Compact, extremely red, bright in the mid-infrared but nearly invisible at shorter wavelengths. They showed up in fields across the sky, not as rare anomalies but as a population. Hundreds of them scattered through early survey data. Some were distant, sitting at redshifts above 5, meaning we were seeing them as they existed when the universe was less than 1 billion years old. Others sat even further back, at redshifts approaching 10 or higher, and they were strange in a way that didn't match any of the objects Hubble had found. Too red to be normal star-forming galaxies. Too compact to be anything but point sources, like stars, except stars don't sit at cosmological distances. Too bright in certain wavelengths to be explained by any standard stellar population. Astronomers started calling them little red dots. Not an official name, just a descriptor that stuck because it captured what they looked like on screen. Little red dots. For a while, no one knew what they were. Dusty galaxies, maybe, with all their starlight absorbed and re-radiated at longer wavelengths, or extremely old galaxies whose stars had all evolved into red giants, or something else entirely. The data didn't fit neatly into any box, and the more Webb looked, the more of them it found. In those first months, there was a strange mix of excitement and unease running through the community. Excitement because finding something unexpected is what telescopes like Webb are for. That's the whole point. Build a better instrument and it shows you things you didn't know were there. But unease because the little red dots weren't just unexpected, they were numerous. And numerous means common, and common means important. If there are thousands of these objects scattered across the high redshift universe, they're not a fluke. They're a population, and if they're a population, they have to fit into the story of how galaxies and black holes and stars came together in the first place. Except the story didn't have a place for them. Not yet. Not until someone figured out what they actually were. The deep fields kept coming. CEERS, the Cosmic Evolution Early Release Science Survey, scanned a region near the extended growth strip, a well-studied patch of sky where Hubble had already spent years staring. JADES, the JWST Advanced Deep Extragalactic Survey, went even deeper, targeting areas where gravitational lensing could boost the signal from the faintest objects. And in every field, the little red dots kept showing up. Compact, red, bright, wrong. Some of them sat at distances where galaxies were supposed to be small and faint and still assembling. These weren't. They looked mature, or at least energetic, as if something inside them was already running at full tilt barely 500 million years after the universe began. One of the most unnerving aspects of the discovery was how quickly it became clear that Hubble had been blind to them. Not because Hubble was broken or poorly designed, but because its instruments simply couldn't see that far into the infrared. The little red dots emit most of their light at wavelengths longer than Hubble's detectors were sensitive to. They were always there. Hubble just couldn't pick them up. Webb could. And the moment it did, an entire population of objects that had been invisible for the entire history of infrared astronomy suddenly appeared all at once, like turning on a light in a dark room and realizing the room was full. By late 2022, the first follow-up studies were starting to come in. Spectroscopy, the detailed splitting of light into wavelengths, began to reveal what these objects actually were. And the answer, when it came, was somehow both a relief and a new problem. They weren't galaxies, not in the traditional sense. They were black holes. Or more precisely, they were the light from material falling into black holes, heated to millions of degrees as it spiraled inward, glowing so brightly that it outshone every star in the surrounding galaxy. Little red dots weren't little galaxies. They were little monsters. Compact, feeding, growing, and there were thousands of them, scattered across the early universe like seeds waiting to grow into something much, much larger. The promise of Webb had always been to see the first galaxies, the first stars, the first light. What it found instead was something older, something stranger, something that suggested the universe had gotten a head start on building its most extreme objects. And the deeper Webb looked, the more it became clear that the early universe was not the quiet, orderly place the simulations had predicted. It was loud, it was chaotic, and it was full of little red dots that were about to rewrite the rules. The first major surveys had names that sounded like acronyms pulled from a government filing cabinet, but they represented something closer to archaeological digs conducted at the edge of space-time. CEERS, JADES, Uncover. Each one was a coordinated campaign involving dozens of scientists, hundreds of hours of telescope time, and a shared obsession with answering a single question: what did the universe actually look like when it was young? Not what the models said it should look like. What was actually there? And the answer, when it started coming in, was not what anyone had written down in the proposal documents. CEERS launched first. The acronym stands for Cosmic Evolution Early Release Science, and the name gives away the strategy. Early release science programs are designed to get data into the hands of the astronomical community as fast as possible, usually within a few months of observation. The idea is to test the telescope's capabilities, demonstrate what it can do, and give everyone a taste of what's coming so they can start planning their own studies. CEERS was one of 13 such programs approved before Webb even launched, and it was explicitly built around speed. Get the data, process it, release it, let the science begin. The survey targeted a region of sky near the extended growth strip, a patch of the northern sky that Hubble and other telescopes had already studied extensively. Astronomers like working in areas where they already have data because it gives them a baseline. You know what Hubble saw. Now point Webb at the same spot and compare. Anything new that shows up is something Hubble couldn't detect, which immediately tells you it's either very faint, very red, or both. The extended growth strip had been mapped in visible light, near infrared, X-rays, radio. It was one of the most thoroughly observed pieces of cosmic real estate available. If Webb was going to find something Hubble missed, this was a good place to look. CEERS used NARCam, Webb's primary imaging camera, to take deep exposures across multiple infrared filters. Filters are just pieces of glass or coated material that only let specific wavelengths of light through. By taking images in several filters and comparing the brightness of each object across those wavelengths, astronomers can reconstruct the object's spectrum, at least crudely. It's not as precise as splitting the light with a spectrograph, but it's much faster. You can survey a wide area and pick out interesting targets for follow-up. Enigma's field of view is about 2.5 arc-minutes across. For scale, the full moon is about 30 arc-minutes wide, so each Enigma image covers roughly 1/10 of the moon's diameter. Not huge, but large enough to capture hundreds of galaxies in a single shot if you're looking at a dense field. The team took exposures at wavelengths ranging from about 0.9 microns out to 5 microns, covering the near and mid-infrared. At those wavelengths, Webb can see galaxies whose light has been redshifted far beyond what Hubble's detectors could handle. A galaxy that emits most of its light in the ultraviolet, the kind of light you'd expect from young hot stars, shifts into the visible range for objects at moderate redshift. Hubble sees those just fine, but push that same galaxy out to a redshift of 7 or 8, and the ultraviolet light gets stretched all the way into the infrared. Hubble's cameras go blind. Webb's wake up. The first CEERS images came down in June 2022, less than 6 months after Webb reached its orbital position. The data were released publicly in September, and almost immediately, astronomers started seeing things that didn't fit. Compact red sources scattered throughout the field, dozens of them. Some were obvious high redshift galaxy candidates. Their light stretched so far into the infrared that they only showed up in the reddest filters, but others were stranger. They were red, yes, but also unusually bright in the mid-infrared compared to shorter wavelengths. Their colors didn't match the expectations for normal star-forming galaxies. Star-forming galaxies have a predictable spectrum. Young stars are blue and hot. Older stars are red and cool. Dust absorbs blue light and re-emits it in the infrared. Put those ingredients together, and you get a galaxy that glows across a range of wavelengths in a fairly orderly way. The CEERS red sources didn't follow that pattern. They were too red in a way that felt off. The initial hypothesis was dust. Dust can do strange things to light. It scatters and absorbs shorter wavelengths preferentially, letting redder light pass through. If a galaxy is forming stars inside a thick cloud of dust, the ultraviolet and visible light from those stars gets absorbed and re-radiated at longer wavelengths. The result is a galaxy that looks much redder than it actually is. Dusty galaxies are common in the nearby universe. Astronomers have been studying them for decades. Some of the most luminous galaxies known are completely shrouded in dust, glowing brilliantly in the infrared while remaining nearly invisible in optical light. So the first instinct was to assume these CEERS red sources were just distant, dusty galaxies. Problem solved. Move on. Except the numbers didn't quite work. Dusty galaxies tend to be large. The dust is spread out over kilonewtons, filling the space between stars. The CEERS red sources were small, compact, more like point sources, the way a single star looks, than extended objects, the way a galaxy looks. That's strange because if you're seeing a whole galaxy shrunk down to a point, it means either the galaxy is extremely far away, so far that even a large galaxy appears tiny, or it's genuinely compact, meaning all of its light is coming from a very small region. Both possibilities raised questions. If the objects were extremely distant, they'd have to be extraordinarily luminous to be detected at all. If they were compact, something unusual had to be concentrating all that energy into a small space. The team ran photometric redshifts, a technique that estimates distance by comparing an object's brightness across multiple filters and finding the best fit model. Photometric redshifts aren't perfect. They can be fooled by unusual spectra or unexpected emission lines, but they're fast and they work reasonably well for large samples. The CEERS red sources came back with estimated redshifts ranging from about 5 to over 10. Redshift 5 corresponds to seeing the universe as it was about 12.5 billion years ago. Redshift 10 pushes back to around 13.2 billion years, just 480 million years after the Big Bang. Those are not casual distances. At those epochs, the universe was still in its infancy. Galaxies were supposed to be small and dim and still assembling. These objects were bright, compact, and showing up in numbers that made them look like a population rather than a handful of oddities. Then JADES started producing data. JADES stands for JWST Advanced Deep Extragalactic Survey, and it was designed to go even deeper than CEERS, where CEERS aimed for breadth, covering a relatively wide area to test Webb's capabilities. JADES aimed for depth, longer exposures, fainter objects, and critically, spectroscopy. JADES wasn't just taking pictures, it was splitting light into spectra using NIR spec, Webb's near-infrared spectrograph, to measure the exact redshifts of distant galaxies and analyze the physical conditions inside them. Spectroscopy is slower than imaging. You can only observe one object or a handful of objects at a time, but it gives you information imaging alone can't provide. The presence or absence of specific emission lines, the widths of those lines, the ratios of different elements, all of that tells you what's happening inside the object, not just where it is. JADES targeted two fields. One was part of the Hubble ultra-deep field, arguably the most famous patch of sky in all of astronomy, a region Hubble had stared at for weeks back in the mid-2000s to produce the deepest visible light image ever taken. The other was the Good South field, another well-studied region with extensive archival data. Both fields had been chosen specifically because they were already deep. JADES wasn't discovering new territory. It was going back to familiar ground with better tools. The survey used NIRCam to image the fields in 9 filters, ranging from 0.9 microns out to 5 microns, with total integration times reaching more than 80 hours in some filters. 80 hours is a long time for a space telescope. For comparison, a typical Hubble observation might last a few orbits, maybe a few hours total. JADES was camping out, and the depth showed. Objects that were barely visible in Hubble images, or completely invisible, popped out in the JADES data. Faint smudges resolved into galaxies, empty patches of sky filled with distant sources. And scattered among those sources were more of the same compact red objects CEERS had found, dozens more, some of them sitting at photometric redshifts above 7, a few above 10, and they kept showing the same strange properties: too red, too compact, too bright in the mid-infrared. JADES followed up the imaging with spectroscopy, targeting some of the reddest and most distant candidates. Spectroscopy doesn't just confirm the distance, it reveals the spectrum, and the spectrum is where things got interesting. When the first spectra came back, they showed broad emission lines, very broad. Emission lines are bright features in a spectrum where gas is glowing at specific wavelengths. Hydrogen, for example, produces a characteristic set of lines, so does oxygen, nitrogen, carbon. The presence of those lines tells you what elements are present in the gas. The width of those lines tells you how fast the gas is moving. Narrow lines mean the gas is sitting still or moving slowly. Broad lines mean the gas is moving fast, very fast, thousands of kilometers per second. Broad lines in a galaxy's spectrum usually mean one thing: there's a black hole at the center, and gas is falling into it. As the gas spirals inward, it accelerates, reaching velocities close to a significant fraction of the speed of light by the time it crosses the event horizon. The motion Doppler shifts the light emitted by the gas, smearing the emission lines out into broad features. The broader the line, the faster the gas is moving and the closer it is to the black hole. Narrow lines come from gas farther out, moving more slowly in the galaxy's gravitational field. Broad lines come from gas right at the edge of the abyss, and the JADES spectra showed lines so broad they could only be explained by gas moving at several thousand kilometers per second, which meant there was a black hole down there feeding. This was the moment the little red dots stopped being a curiosity and started being a problem. They weren't dusty star-forming galaxies, they were active galactic nuclei, or AGN, the term astronomers use to describe a galaxy with a supermassive black hole that's actively accreting matter. And they were everywhere, not rare, not confined to a few special objects, common, a population, scattered across the high redshift universe in numbers that suggested they were a significant component of the early cosmic ecosystem. And that didn't match the standard story. Supermassive black holes in the early universe were supposed to be rare. They were supposed to take time to grow. You start with a stellar mass black hole, maybe a few tens of solar masses, formed from the collapse of a massive star. Over hundreds of millions of years, it accretes gas and grows. Eventually, after billions of years, it becomes supermassive, weighing millions or billions of times the mass of the Sun. That's the timeline the models predicted. Slow growth, gradual accumulation, no shortcuts. The little red dots were sitting at redshifts where the universe was less than 1 billion years old. Some were even younger, closer to 500 million years after the Big Bang, and they were already feeding, already glowing with the light of accreting black holes. That didn't give them enough time to grow the slow way. Either the black holes had started out much larger than a stellar mass seed, or they had grown much faster than the models allowed, or both. And the sheer number of them made it worse. If there were thousands of these objects scattered across the sky, the early universe must have been producing supermassive black holes on an industrial scale, not as rare flukes, but as routine products of whatever process was assembling the first galaxies. The Uncover program added another layer. Uncover stands for Ultra-Deep Near-Spec and Near-Cam observations from the EROs, and it targeted gravitationally lensed fields. Lensing clusters act as natural magnifiers, bending and amplifying the light from background galaxies. Uncover used that magnification to push even deeper, detecting objects so faint they would have been invisible even to Webb without the boost from the lens. The program combined NEMIR imaging with NEMIR spec spectroscopy, focusing on objects in the lensed background that Hubble had either barely detected or missed entirely. Among the lensed objects, more little red dots, some of them magnified enough that their spectra could be studied in detail. And the spectra kept telling the same story. Broad lines, fast-moving gas, black holes. The magnification from the lens also allowed astronomers to measure the physical sizes of the objects more precisely. The answer came back the same every time: compact, less than 1 kilonewton across in most cases. For scale, the Milky Way is about 100,000 light-years across. These objects were 100 times smaller, yet they were shining with luminosities that rivaled entire galaxies. That's the signature of an active galactic nucleus. All the light is coming from a tiny region around the black hole, not from stars spread across a galactic disk. The galaxy might still be there, somewhere in the background, but it's being outshone by the monster at its core. The redness was still a puzzle. Even with a black hole at the center, why did these objects look so red? Normal AGN emit across a broad range of wavelengths, from X-rays down through the optical and into the infrared. If you're seeing an AGN with a clear view of the central engine, it should be bright in the ultraviolet and visible light, not just the infrared. The fact that the little red dots were so red suggested something was blocking the shorter wavelengths. Dust was the obvious culprit. A thick torus of dust and gas surrounding the black hole could absorb the ultraviolet and optical light and re-radiate it in the infrared. Astronomers have known for decades that many AGN are heavily obscured. We see them edge on through their dusty equators, and all the high-energy light gets filtered out. What reaches us is the infrared glow of heated dust. That model works for nearby AGN, and it probably works for at least some of the little red dots, but it doesn't explain all of them. Some of the spectra showed broad emission lines that should only be visible if you have a relatively clear view of the central region. If the dust were thick enough to block most of the optical light, it should also block the emission lines, but the lines were there, bright and broad. So either the dust is distributed in a way that lets some light through while blocking the rest, or there's another source of redness we haven't accounted for. One possibility is that the host galaxies themselves are extremely dusty, not just the region around the black hole, but the whole galaxy. If the galaxy is in the middle of a vigorous burst of star formation, it would be filled with dust produced by those stars. The black hole's light would have to travel through that dust to reach us, and by the time it did, most of the blue and ultraviolet light would be absorbed. That could make the object look red even if the AGN itself is unobscured. Another possibility is that some of the redness is intrinsic to the black hole's emission. If the accretion disk is cooler than usual, or if the black hole is rotating in a way that changes the geometry of the emitted light, the spectrum could naturally peak in the infrared rather than the optical. Both explanations are plausible. Neither one is proven. The data so far don't cleanly favor one over the other. What became clear by the end of 2022 was that the little red dots were not a fluke. They were showing up in every deep survey Webb conducted. CEERS found them, JADES found them, Uncover found them. Other programs, smaller surveys targeting different fields, found them too. They appeared in lensed fields and unlensed fields. They appeared at redshifts from about 5 all the way out past 10. They appeared in regions of sky that Hubble had stared at for years without seeing anything unusual, and they all shared the same basic properties: compact, red, bright in the mid-infrared, broad emission lines indicating black hole activity, and distances that placed them in the first billion years of cosmic history, an era when black holes that size were not supposed to exist in those numbers. The scientific literature began filling with papers trying to make sense of the population. Some studies argued that the little red dots represented a transitional phase in galaxy evolution, a brief period when black holes grew faster than their host galaxies and temporarily outshone them. Others suggested they were the seeds of the supermassive black holes we see in the centers of massive galaxies today, caught in the act of rapid growth. A few papers floated more exotic ideas, like the possibility that some of the objects weren't growing from stellar mass seeds at all, but had formed as intermediate mass black holes directly from collapsing gas clouds in the early universe. Every model had to explain the same basic facts. The objects were numerous, they were compact, they were feeding, and they were young. By early 2023, the community had started converging on a rough consensus. The little red dots were AGN. That much was clear from the spectra, but they were a specific kind of AGN, one that didn't fit neatly into the categories astronomers had been using for decades. They weren't quasars, at least not in the classical sense. Quasars are bright, relatively unobscured AGN that shine across the entire electromagnetic spectrum. They're some of the most luminous objects in the universe, and they've been studied since the 1960s. The little red dots were dimmer than typical quasars, at least in the optical and ultraviolet, and much redder. They also weren't typical Seyfert galaxies. Another class of AGN named after the astronomer Carl Seifert, who first catalogued them in the 1940s. Seiferts are AGN in nearby galaxies, and they come in two flavors. Type 1 Seiferts show broad emission lines, meaning you're seeing the central engine. Type 2 Seiferts show only narrow lines, meaning the central engine is hidden behind dust. The little red dots had broad lines, which should make them Type 1, but they looked red, which suggested heavy obscuration, more like Type 2. They were sitting in a grey area between categories, which usually means the categories themselves need updating. The realization that Webb had found a whole new population of objects, one that had been invisible to every previous telescope, sent a ripple through the field. It wasn't panic, it was something closer to recalibration. Models that had worked fine for explaining Hubble's observations suddenly had a new constraint to satisfy. Any theory of how galaxies and black holes formed in the early universe now had to account for the little red dots. Where did they come from? How did they grow so fast? Why were there so many of them? And what did they turn into? Because the little red dots weren't the endpoint. They were young. Whatever they were at redshift 7 or 8, they had another 13 billion years ahead of them to evolve, merge, grow, and become something else. And if you followed that thread forward, tracing their descendants into the present day, you started to wonder whether the supermassive black holes sitting in galaxies today, the ones weighing billions of solar masses, the ones like the black hole in the center of the Milky Way or the monster at the heart of M87, might have started as little red dots, compact and feeding and red, hiding in the early universe where no telescope could see them until Webb finally turned on its golden mirror and looked. There's a difference between seeing something and understanding it. You can point a camera at a distant light and capture an image. The light registers, the telescope records it. The data goes into a file somewhere and gets stored on a server with a backup in case the server fails. That's seeing. It's mechanical, it's passive. The telescope doesn't care what the light means, it just collects photons and counts them. Understanding requires more. It requires asking the light where it came from, what it passed through, and what produced it in the first place. You have to interrogate the photons, and the way you do that is with spectroscopy. Spectroscopy is one of those techniques that sounds technical until you realize you've been doing a version of it your entire life. Every time you've watched a sunset turn orange, you've witnessed spectroscopy in action. The sun's light passes through the atmosphere, and the air scatters the blue wavelengths more than the red ones. What reaches your eyes at the horizon is the leftover red light, the stuff that made it through. Your brain doesn't do the math, but the physics is there whether you notice it or not. Astronomers do the same thing, except instead of just watching the color change, they split the light apart into its component wavelengths and study the pattern. Every element, every molecule, every atom in the universe has a unique spectral fingerprint. Hydrogen glows at specific wavelengths. So does helium, carbon, oxygen, iron. When those elements are heated or ionized, they emit light at precise colors, producing bright lines in the spectrum. When light passes through a cloud of cooler gas, the gas absorbs those same wavelengths, producing dark lines. The pattern of bright and dark lines is as distinctive as a barcode on a product at a grocery store. Scan it and you know what you're looking at. In astronomy, spectroscopy tells you what an object is made of, how hot it is, and how fast it's moving. The composition comes from the lines themselves. Hydrogen lines mean hydrogen is present, oxygen lines mean oxygen. The temperature comes from which lines are brightest. Hotter gas ionizes more completely, stripping electrons off atoms and changing which wavelengths get emitted. The motion comes from the Doppler shift. If the object is moving toward you, its light gets compressed, and the lines shift toward the blue end of the spectrum. If it's moving away, the light stretches and the lines shift red. Measure the shift and you know the velocity. It's one of the most powerful tools in all of physics, and it works the same way whether you're studying a car engine or a galaxy 10 billion light years away. For the little red dots, imaging alone could only take the story so far. Pictures told astronomers where the objects were and roughly how bright they appeared in different infrared filters. That was enough to estimate distances and flag them as unusual. But pictures couldn't explain what was producing the light. Were these compact star-forming galaxies churning out new suns at a furious rate? Were they old galaxies whose stars had all aged into red giants? Were they dusty galaxies with all their starlight absorbed and re-radiated at longer wavelengths? Or were they something else entirely, something that didn't fit into any existing category? The only way to answer that was to take spectra, and that required time, precision, and an instrument sensitive enough to split the faint infrared light of objects sitting more than 10 billion light-years away. Webb carries exactly that instrument. It's called NINISPEC, the Near-Infrared Spectrograph, and it was built specifically to study distant galaxies in detail. NINISPEC can observe up to around 200 objects simultaneously using a device called a micro-shutter array, a grid of tiny shutters each about the width of a human hair that can be opened or closed individually to let light through from specific targets while blocking everything else. Think of it like a customizable filter that creates hundreds of tiny windows, each one aligned with a different galaxy in the field of view. The light from each galaxy passes through its dedicated window, gets dispersed by a prism or grating into a spectrum, and lands on a detector. The result is a stack of spectra, one for each object, all collected in a single observation. It's astonishingly efficient compared to older techniques where you had to point a single slit at one object at a time and observe each target separately. With NIRSpec, you can survey an entire field in the time it used to take to study a handful of galaxies. The catch is that spectroscopy is slow. It requires long exposures because you're not just collecting light. You're spreading that light out across a range of wavelengths, which makes each individual wavelength much fainter. Imagine taking a photograph and then stretching it horizontally until it's 100 times wider. The image is still there, but it's dimmer because the same amount of light is now spread across a much larger area. Spectra work the same way. To get a clean spectrum of a faint object, you need to stare at it for hours, sometimes tens of hours, letting the photons accumulate until the signal is strong enough to rise above the noise. For the little red dots, which were already faint to begin with, that meant serious telescope time. And telescope time on Webb is expensive, not in dollars, though there's that too, but in opportunity cost. Every hour spent observing one set of targets is an hour not spent observing something else. Proposals get reviewed, priorities get set, and the competition is fierce because every astronomer in the world wants a piece of Webb's schedule. By late 2023, several teams had secured the time they needed and begun taking spectra of the little red dots. One of the largest efforts was a program called RUBIES, which stands for something long and technical that doesn't matter as much as what the program actually did. RUBIES aimed to collect spectra for thousands of distant galaxies across multiple fields, including many of the compact red sources flagged by earlier imaging surveys. The observations ran from January through December 2024 and used nearly 60 hours of Webb's time. 60 hours is a significant investment for any program, and it reflected how seriously the community was taking the mystery. The little red dots weren't just a curiosity anymore. They were a population, and if you're going to understand a population, you need statistics. You need to observe not just a few objects, but dozens, ideally hundreds, so you can see what's typical and what's rare. The first spectra came back in early 2024, and they were strange, not bad, not unclear, strange in a way that immediately changed the conversation. The key feature was the width of the emission lines. Emission lines are the bright spikes in a spectrum where gas is glowing at specific wavelengths. In a normal star-forming galaxy, those lines are relatively narrow because the gas producing them is moving slowly, maybe a few tens of kilometers per second as it drifts through the galaxy's interstellar medium. The motion Doppler shifts the light slightly, but not enough to smear the lines out by much. They stay sharp. In an active galactic nucleus, where a supermassive black hole is feeding, the story is different. The gas near the black hole is moving fast, very fast, thousands of kilometers per second, as it spirals inward, accelerating under the black hole's gravity. The motion Doppler shifts the emitted light by large amounts. Gas moving toward us produces light that's blue shifted. Gas moving away produces light that's red shifted. When you add up all the light from gas moving in every direction around the black hole, the result is a broad emission line, a feature that's been stretched and smeared across a wide range of wavelengths. The broader the line, the faster the gas is moving, and the closer it is to the black hole. The little red dot spectra showed very broad lines. Not just a little broad, very broad. Lines that had been stretched across hundreds or even thousands of kilometers per second worth of velocity. The shape of the lines didn't look like a sharp spike. They looked more like a shark's tooth, one researcher said, with a steep rise on one side and a long tail stretching out on the other. That asymmetry is another signature of an accretion disk, the spinning disk of gas and dust that forms around a black hole as material falls in. Gas on the side of the disk that's rotating toward us appears blue-shifted. Gas on the side rotating away appears red-shifted. The combined emission produces a line profile with a characteristic shape, and the little red dot spectra matched it almost perfectly. This was the moment the interpretation flipped. The little red dots weren't galaxies dominated by stars, they were galaxies dominated by black holes. Or more precisely, they were galaxies where the light from the central black hole was so bright that it outshone everything else. The stars were probably still there, scattered throughout the galaxy, but they were invisible in the glare. It's the same effect you get when you try to photograph a candle sitting next to a searchlight. The candle is real, it's producing light, but the searchlight drowns it out completely. The black holes in the little red dots were the searchlights, and the galaxies around them were the candles. Active galactic nuclei have been known since the 1960s, when astronomers first identified quasars, mysterious point sources of light that looked like stars, but were actually the cores of distant galaxies powered by supermassive black holes. Over the decades, the picture became more refined. Not all AGN look the same. Some are bright across the entire electromagnetic spectrum, from radio waves to X-rays. Others are heavily obscured by dust, glowing mostly in the infrared. Some have broad emission lines. Others have only narrow lines. The differences come down to geometry and viewing angle. If you're looking straight down into the accretion disk, you see the central engine clearly. Broad lines, high luminosity, little obscuration. If you're looking edge-on, the thick torus of dust and gas surrounding the black hole blocks your view. The broad line region is hidden, and all you see are the narrow lines from gas farther out, moving more slowly. Astronomers classify AGN into types based on these features. Type 1 AGN have broad lines. Type 2 AGN have only narrow lines, and there are intermediate cases that blur the boundaries. The little red dots, based on their spectra, were clearly Type 1 AGN. They had broad lines, which meant the central engine was at least partially visible, but they were also very red, which suggested heavy dust obscuration. That combination was unusual. If the dust is thick enough to absorb most of the optical and ultraviolet light, it should also block the broad line region from view. But the broad lines were there, bright and clear. So either the dust was distributed in a patchy way, leaving some sightlines open while blocking others, or the redness was coming from somewhere else. One possibility is that the host galaxies themselves were extremely dusty, filled with dust produced by intense star formation. The black hole's light would have to travel through that dust to reach us, and by the time it did, much of the blue light would be absorbed. Another possibility is that some of the redness is intrinsic to the AGN itself, a result of the accretion disk being cooler or more geometrically thick than usual. Both explanations are plausible, and the data so far don't clearly favor one over the other. What the spectra did make clear is that the little red dots were feeding. Black holes grow by accreting matter, pulling in gas and dust from their surroundings. The process is messy and violent. As material spirals inward, it heats up through friction, reaching temperatures of millions of degrees. At those temperatures, the gas glows across a wide range of wavelengths, producing the intense luminosity that characterizes an AGN. The broad emission lines are a direct signature of that process. They tell you that gas is falling into the black hole right now, at this moment, moving at speeds that can only be explained by the immense gravity near the event horizon. The little red dot spectra weren't showing you a dormant black hole sitting quietly at the center of a galaxy. They were showing you a black hole in the act of feeding, consuming matter, and shining brightly as a result. One object in particular stood out. It was nicknamed the Cliff, a name derived from the sharp spectral break in its infrared colors, and it had been highlighted in July 2024 as an extreme example of a little red dot. The light reaching us from the cliff had been traveling for 11.9 billion years, meaning we were seeing the object as it existed when the universe was less than 2 billion years old. Its spectrum showed exceptionally broad emission lines, some of the broadest observed in any of the little red dots surveyed so far. The gas near its central black hole was moving at several thousand kilometers per second, a velocity that placed it firmly in the realm of a rapidly accreting supermassive black hole. The cliff wasn't an outlier. It was an extreme case along a spectrum, but it sat within the same population as the other little red dots. Its existence proved that by the time the universe was less than 2 billion years old, supermassive black holes weighing potentially millions of solar masses were already in place and feeding vigorously. The discovery of broad lines in a significant fraction of the little red dots was described by several researchers as the strongest piece of evidence yet that these objects were powered by black holes rather than stars. It wasn't just a hypothesis anymore. It was a conclusion supported by direct spectroscopic measurements. The lines were there, the velocities were there, the geometry matched, and the numbers were piling up. By mid-2024, spectra had been obtained for dozens of little red dots across multiple surveys, and the pattern held. Not every single one showed broad lines. Some showed narrower features, more consistent with star formation or less vigorous AGN activity, but a significant fraction, enough to matter, showed the broad line signature that pointed unambiguously to a feeding black hole. One astronomer narrating the findings described the interpretation plainly. The very broad lines implied that whatever was happening in the center seemed to involve super-powerful black holes. That quote made it into several summaries of the research because it captured the essence of what the spectra were revealing without overcomplicating the story. Super-powerful black holes, not small ones, not modest ones. Massive black holes, already grown to significant size, sitting at the centers of galaxies that were themselves still young and small. The mismatch between the age of the universe and the size of the black holes was the puzzle that needed solving, and the spectra were the evidence that proved the puzzle was real. Spectroscopy also allowed astronomers to estimate the masses of the black holes. The relationship between the width of the broad emission lines and the black hole's mass is well established. Broader lines mean faster gas motion, and faster motion at a given distance from the black hole means a more massive black hole. It's not a perfect measurement. It relies on assumptions about the geometry of the accretion disk and the distance of the emitting gas from the black hole. But it's a reasonable estimate, and it's been calibrated against other methods in nearby galaxies where the black hole masses can be measured more directly. For the little red dots, the masses came back in the range of millions of solar masses, not tens of millions, not billions, but solidly in the supermassive category. Those are black holes comparable in mass to the one sitting at the center of the Milky Way, which weighs about 4 million solar masses. Except the little red dots were being observed at redshifts where the universe was a fraction of its current age. The Milky Way's black hole had 13.8 billion years to grow. The little red dot black holes had less than 2 billion. They'd done it faster. Not every spectrum was clean. Some of the little red dots were so faint that even with hours of exposure time, the spectra came back noisy, with weak lines barely visible above the background. Others had spectra that were harder to interpret because multiple physical processes seemed to be happening at once. Broad lines from the AGN, narrow lines from star-forming regions elsewhere in the galaxy, absorption features from dust. Disentangling those components required careful modeling, and in some cases the conclusions were tentative rather than definitive, but the overall picture was consistent. The majority of the little red dots with clear spectra showed signatures of AGN activity, and a significant subset of those showed the very broad lines that indicated rapid accretion onto a supermassive black hole. The Rubies campaign, with its nearly 60 hours of observing time and spectra for 4,500 distant galaxies, provided the statistical foundation the field needed. Before Rubies, the little red dots were intriguing but poorly understood. After Rubies, they were a documented population with measurable properties. The spectra showed that these weren't rare flukes. They were common at high redshift, making up a non-negligible fraction of the AGN population in the early universe. And their compactness, their redness, and their broad emission lines all pointed to a specific evolutionary stage. They were young supermassive black holes in the process of growing, surrounded by dusty gas-rich galaxies, feeding rapidly and shining brightly despite being buried under layers of obscuring material. The spectroscopic evidence also raised new questions. If these black holes were already so massive so early, where did they come from? The standard model assumes black holes grow from stellar mass seeds, the remnants of the first massive stars, but the growth rate required to reach millions of solar masses in less than 1 billion years pushes the limits of what accretion models allow. Black holes can only grow so fast before the radiation from the infalling material pushes back against the incoming gas, choking off the supply. It's called the Eddington limit, and it sets an upper bound on how quickly a black hole can gain mass. Feed it too fast, and it becomes so luminous that the radiation pressure blows the gas away. To grow a 1 million solar mass black hole from a stellar mass seed in less than 1 billion years, you have to accrete at or near the Eddington limit continuously. No breaks, no pauses, just constant feeding. That's possible in theory, but it requires very specific conditions. The gas supply has to be steady. The environment has to be dense. And there can't be any disruptive events like galaxy mergers or supernova-driven winds that scatter the gas before it reaches the black hole. Whether the early universe provided those conditions consistently enough to explain thousands of little red dots scattered across the sky was an open question. The alternative was that the black holes didn't start small. If they began as intermediate mass seeds, already weighing tens of thousands or even hundreds of thousands of solar masses, the growth problem becomes much easier. Starting with a head start gives you more time to reach supermassive status, and the required accretion rate drops to something more manageable. But intermediate mass seeds are exotic. They can't form from normal stellar collapse. You need a different mechanism, something like direct collapse, where a giant cloud of gas skips the star formation stage entirely and collapses straight into a black hole. Direct collapse is theoretically possible under the right conditions, but it requires a very specific environment. The gas has to be hot enough and dense enough to collapse quickly, but not so hot that it fragments into stars first. And it has to avoid cooling down too fast, because once the gas cools, it can form molecules like hydrogen molecules that radiate energy away and allow the cloud to break apart into smaller clumps. If direct collapse happened in the early universe, it would solve the growth problem, but proving it happened is harder. The little red dot spectra told you that massive black holes existed early on. They didn't tell you how those black holes formed in the first place. What the spectra did confirm, beyond any reasonable doubt, was that the little red dots were not what they first appeared to be. They weren't galaxies, they were monsters. Compact, feeding, buried under dust, shining with the light of gas falling into black holes at thousands of kilometers per second. The imaging surveys had found them. The spectroscopy unmasked them. And once the masks came off, the question shifted from what are they to how did they get there and what happens next. Because the little red dots were just the beginning. They were young, they were growing. And in 13 billion years, after the dust cleared and the feeding stopped, and the galaxies around them matured, they would become something much, much larger. The spectra had identified the seeds. The next step was understanding what they would grow into, and why the early universe had planted so many of them in the first place. The spectroscopic campaign wasn't finished. More observations were already scheduled. More little red dots were being targeted. And every new spectrum added another data point to the growing picture of what the early universe actually looked like when the first supermassive black holes were just getting started. But even with the data still coming in, one thing was already clear. The broad emission lines had done their job. They'd revealed the monsters hiding inside the little red dots. And now that we knew the monsters were there, the question became not whether they existed, but how they managed to grow so large so fast, and whether the light we were seeing, the infrared glow of heated dust and accreting gas, was only part of the story. Because if there was one thing the spectra couldn't see, it was what was happening behind the veil, and that's where the X-rays came in. Spectroscopy told you there were black holes. The broad emission lines made that clear. Gas moving at thousands of kilometers per second doesn't just happen by accident. You need gravity, extreme gravity, the kind that can only come from a supermassive black hole sitting at the center of a galaxy and pulling matter inward at velocities approaching a significant fraction of the speed of light. The spectra revealed the motion. They showed you the Doppler shifts, the smeared-out emission features that could only be explained by gas spiraling into an accretion disk. But spectroscopy has limits. It tells you what's glowing. It doesn't tell you what's hiding. And in the case of the little red dots, something was definitely hiding. The redness was the clue. Normal active galactic nuclei, the kind astronomers have been studying for decades, glow across a broad range of wavelengths. They're bright in the ultraviolet because the gas near the black hole is heated to hundreds of thousands of degrees. They're bright in the optical because that hot gas emits visible light. They're bright in the infrared because dust surrounding the system absorbs some of that light and re-radiates it at longer wavelengths. And they're bright in X-rays because the innermost regions of the accretion disk, where the gas reaches temperatures of millions of degrees just before crossing the event horizon, emit high-energy photons that can punch through almost anything. A typical unobscured AGN is a multi-wavelength powerhouse. It shows up everywhere you look, from radio waves to gamma rays. The little red dots didn't behave that way. They were bright in the infrared. That part was clear from Webb's imaging. But they were faint or completely invisible in the optical and ultraviolet. Hubble couldn't see most of them. Shorter wavelength observations either missed them entirely or detected only faint smudges. That mismatch, bright in the infrared but dim everywhere else, pointed to one explanation. Something was blocking the shorter wavelengths. The black holes were there. The accretion was happening. The gas was glowing. But between the glowing gas and our telescopes, there was a wall. A thick, dusty, opaque wall that absorbed the ultraviolet and optical light before it could escape, leaving only the infrared glow of heated dust visible from the outside. Astronomers have a term for this. They call it obscuration, and it's one of the most common features of active galactic nuclei. Not all AGN are obscured. Some are naked, their central engines fully exposed to our view. Those are the ones that show up as bright quasars, glowing across the entire electromagnetic spectrum. But many AGN, perhaps the majority, are buried inside thick cocoons of gas and dust. The cocoon surrounds the black hole and its accretion disk, forming a donut-shaped structure called a torus. If you're looking at the AGN from above or below, you can see straight down into the central engine. Broad emission lines, high luminosity, clear view. If you're looking edge-on through the torus, the dust blocks your line of sight. The broad line region disappears. The optical and ultraviolet light gets absorbed. All you see is the infrared glow of the dust itself, heated by the light it's blocking. The black hole is still there, feeding just as vigorously as the unobscured ones. You just can't see it directly. The little red dots fit that picture almost perfectly. Compact, red, broad emission lines in at least some cases, meaning the central engine wasn't completely hidden, but red enough that significant obscuration had to be present. The dust wasn't blocking everything, but it was blocking enough to shift the peak of the emission into the infrared. That raised an obvious question. If the dust was thick enough to block most of the optical light, what about the X-rays? X-rays are higher energy than optical or ultraviolet light, and they can penetrate material that would completely block shorter wavelengths. But they're not invincible. Thick enough gas, especially gas with heavy elements like iron mixed in, can absorb X-rays too. If the little red dots were as heavily obscured as their redness suggested, the X-rays might be absorbed as well. In that case, you'd never detect them. The black holes would be completely invisible at high energies, hidden behind walls of gas and dust so thick that nothing could escape except the infrared glow of the dust itself. Or maybe not, because X-rays have a way of sneaking through. Not always. Not in every case, but often enough that if you point an X-ray telescope at a field full of little red dots, you might catch a few of them glowing faintly in high-energy light. And that's exactly what happened. X-ray astronomy is hard. The Earth's atmosphere absorbs X-rays completely, so ground-based telescopes are useless. You have to get above the atmosphere, which means satellites. And X-ray telescopes don't work the way optical telescopes do. You can't just put a mirror in front of a detector and focus the light. X-rays are too energetic. They pass straight through normal mirrors instead of reflecting off them. To focus X-rays, you need specially designed mirrors with surfaces that are almost parallel to the incoming light, grazing the X-rays at shallow angles so they ricochet off instead of punching through. The geometry is tricky, the mirrors are expensive, and the detectors have to be exquisitely sensitive because X-ray sources in space are faint. Even a bright quasar emits far fewer X-ray photons than optical photons. Collecting enough X-rays to build a clear image or spectrum can take hours, sometimes days. The two workhorses of X-ray astronomy are NASA's Chandra X Ray Observatory and the European Space Agency's XMM Newton. Chandra launched in 1999 and has been operating for more than 2 decades. Its mirrors can focus X-rays with extraordinary precision, producing images sharp enough to resolve individual sources separated by less than an arc-second. XMM Newton, launched the same year, has larger mirrors that collect more light, making it better for detecting faint sources or studying the spectra of known objects in detail. Both telescopes have spent years surveying the sky, cataloging X-ray sources and building up archives of observations that astronomers can cross-reference with data from other wavelengths. When the little red dots started appearing in Webb's images, one of the first things researchers did was check whether any of them had been detected in X-rays. The logic was straightforward. If these objects really were obscured AGN, powered by accreting black holes, they should emit X-rays, maybe not as many as an unobscured AGN, but some, enough to show up in deep Chandra or XMM Newton observations if you stared at the same patch of sky long enough. The Webb surveys had targeted well-studied fields like the Good South Field and the Extended Growth Strip, regions that had already been observed at multiple wavelengths, including X-rays. That meant the data were already sitting in archives. All anyone had to do was match the positions of the little red dots with the positions of known X-ray sources and see if anything lined up. The first confirmed match came in early 2024, and it made headlines. The object was called 3DHST AX 12014, a mouthful of a designation that reflected its origins in multiple survey catalogues. It had been flagged as a little red dot in Webb's imaging, sitting at a redshift of about 5.6, meaning we were seeing it as it existed roughly 12.5 billion years ago. Its spectrum, obtained with NIR spec, showed broad emission lines consistent with a black hole accreting gas at high velocity. And when astronomers checked the Chandra archives, they found an X-ray source sitting almost exactly at the same position. The match wasn't ambiguous. The coordinates lined up. The X-ray source was real, not a background contaminant or a random fluctuation in the detector noise. Something at the location of the little red dot was emitting X-rays. That discovery was significant because it provided independent confirmation of what the spectra had suggested. The object wasn't just red because of dust. It was red because it was an obscured AGN, a black hole buried inside a cocoon of gas and dust, feeding and glowing and emitting X-rays despite being hidden from view at shorter wavelengths. The X-rays weren't as bright as you'd expect from an unobscured AGN. They were faint, barely detectable even with Chandra's sensitivity, but they were there, and their presence meant the black hole was real. You can fake redness with dust. You can fake compactness with distance. You can't fake X-rays. X-rays come from gas heated to millions of degrees, and the only thing in the universe that heats gas to those temperatures in such small volumes is a black hole. The detection of 3DHST AGS 12014 in X-rays opened the floodgates. Other teams started cross-referencing Webb's little red dots with X-ray catalogs. and more matches started appearing. Not every little red dot had an X-ray counterpart. Many didn't. Either they were too heavily obscured for the X-rays to escape, or the existing X-ray observations weren't deep enough to detect them, or the black holes were in a quieter phase of accretion and simply weren't emitting as many X-rays at the moment Webb happened to observe them. But a significant fraction, enough to matter, did show up in X-rays. And every detection added weight to the interpretation that these objects were obscured AGN rather than some exotic type of star-forming galaxy. X-ray observations do something optical and infrared observations can't. They cut through the dust. Not completely. Thick enough gas can absorb X-rays too, especially at lower energies. But X-rays are penetrating enough that even a heavily obscured AGN will usually leak some high-energy photons. The amount of X-ray emission you detect tells you how obscured the source is. An unobscured AGN emits X-rays freely, and you see the full luminosity of the central engine. A moderately obscured AGN has its X-rays partially absorbed. You still see a signal, but it's weaker and skewed toward higher energies because lower energy X-rays are more easily absorbed. A heavily obscured AGN, sometimes called Compton thick because the column of gas is so dense that even X-rays start scattering off electrons instead of passing through, barely emits any X-rays at all. You might detect a faint glow, reflected X-rays that have bounced off gas farther from the black hole, but the direct emission from the central engine is completely blocked. The little red dots that showed up in X-rays fell somewhere in the middle. They weren't Compton thick. If they were, Chandra wouldn't have detected them, but they weren't unobscured either. The X-ray luminosities were lower than you'd expect for an AGN of that mass feeding at that rate, which meant some of the X-rays were being absorbed before they reached us. The level of obscuration varied from object to object. Some little red dots had relatively clean X-ray detections, suggesting the line of sight to the black hole was only lightly blocked. Others had much weaker X-ray signals, consistent with heavy but not complete obscuration. The diversity suggested that the little red dots weren't a single uniform population. They were a range of systems at different stages of evolution, with different amounts of gas and dust surrounding their central black holes, viewed from different angles. One of the surprising aspects of the X-ray detections was that they were detectable at all. Heavily obscured AGN are notoriously hard to find because the very thing that makes them interesting, the thick cocoon of gas and dust, also makes them invisible at most wavelengths. Optical surveys miss them because the dust blocks the light. Infrared surveys might catch the glow of the heated dust, but without a spectrum, it's hard to tell whether the infrared emission is coming from an AGN or just a dusty star-forming galaxy. X-ray surveys are one of the few reliable ways to find obscured AGN because X-rays are one of the few types of light that can punch through the obscuration. But even X-ray surveys have limits. If the obscuration is thick enough, the X-rays get absorbed too, and the AGN becomes completely invisible. The fact that the little red dots were showing up in X-rays meant their obscuration was significant but not extreme. They were hiding but not perfectly. The correlation between the little red dots and X-ray detections also helped resolve an ongoing debate about what these objects actually were. In the months after Webb first found them, several alternative explanations had been floated. Maybe they were extremely dusty star-forming galaxies, churning out new stars at a ferocious rate and glowing in the infrared because all the starlight was being absorbed and re-radiated by dust. Maybe they were old galaxies whose stars had all aged into red giants, producing a naturally red spectrum without needing any dust at all. Maybe they were something even more exotic, like primordial black holes that had formed directly from collapsing gas clouds, without ever going through a stellar phase. The X-ray detections didn't rule out all of those possibilities, but they strongly favored the obscured AGN interpretation. Star-forming galaxies don't emit X-rays at the luminosities the little red dots were showing. Old galaxies with red giant stars emit almost no X-rays at all. Primordial black holes, if they existed, would emit X-rays, but their X-ray spectra would look different from what was being observed. The X-ray data fit the obscured AGN model almost perfectly and didn't fit much else. Multi-wavelength astronomy, the practice of observing the same object at different wavelengths and combining the data, has become one of the most powerful tools in modern astrophysics. Every wavelength tells you something different. Optical light shows you stars and ionized gas. Infrared shows you dust and cool objects. Radio waves show you synchrotron emission from relativistic particles. X-rays show you hot gas and accretion onto compact objects. By combining observations across the spectrum, you can build a complete picture of what's happening inside an object. For the little red dots, that picture was coming together. Webb's infrared images showed where they were and how bright they appeared in the mid-infrared. NISPEC spectra showed the broad emission lines that revealed the presence of a black hole, and Chandra's X-ray detections confirmed that the black holes were actively accreting, pulling in gas and heating it to millions of degrees. Each piece of data added a layer to the story, and the story that emerged was one of hidden growth. Obscured accretion, the process by which a black hole grows while buried inside a cocoon of gas and dust, is not a new concept. Astronomers have known for decades that many AGN are heavily obscured and that obscuration is a natural part of black hole evolution. In the early stages of a galaxy's life, gas is abundant, star formation is vigorous, and the environment around the central black hole is messy, filled with dense clouds of gas and dust that block light from escaping. As the black hole feeds, it pulls in gas from its surroundings, growing steadily even though it's invisible to most telescopes. Eventually, the black hole grows powerful enough that the radiation from its accretion disk starts pushing the surrounding gas away. The cocoon begins to clear. Slowly at first, then more rapidly as the radiation pressure builds, the AGN transitions from obscured to unobscured, the dust is blown out, and the black hole emerges as a bright quasar fully visible across the electromagnetic spectrum. This sequence, from buried black hole to visible quasar, is thought to be a standard part of AGN evolution. The little red dots, according to this picture, were being caught in the early phase, the buried phase, before the cocoon had cleared. That interpretation had major implications for understanding how supermassive black holes grew in the early universe. If a significant population of black holes was growing while obscured, hidden behind thick walls of gas and dust, then surveys that only looked at unobscured AGN were missing a large part of the story. The number of AGN you find depends on how you look for them. Optical surveys find unobscured AGN because those are the ones that shine brightly at visible wavelengths. X-ray surveys find both obscured and unobscured AGN because X-rays can penetrate at least some of the obscuration, but even X-ray surveys have limits. If the obscuration is thick enough, the AGN becomes invisible even in X-rays. The little red dots, with their heavy dust obscuration but detectable X-ray emission, suggested there was a whole population of black holes growing in the early universe that previous surveys had missed because they were too obscured to show up in optical light, but not quite obscured enough to disappear completely in X-rays. That realization changed the census. Before Webb, estimates of how many supermassive black holes existed in the early universe were based mostly on finding bright quasars. Quasars are easy to spot because they're luminous. But if quasars represent only the unobscured phase of AGN evolution, And if the obscured phase lasts longer or is more common, then the number of growing black holes in the early universe could be much higher than the quasar counts suggested. The little red dots were the missing piece. They were the obscured black holes that previous surveys had been blind to, and their discovery implied that the early universe was more crowded with feeding black holes than anyone had realized. The X-ray data also provided clues about how fast the black holes were growing. X-ray luminosity is directly tied to accretion rate. The more gas falling into the black hole per unit time, the more X-rays get emitted. By measuring the X-ray luminosity and estimating the black hole's mass from the width of the broad emission lines, astronomers could calculate how fast the black hole was gaining weight. The numbers varied from object to object, but many of the little red dots appeared to be accreting at rates close to or even exceeding the Eddington limit, the theoretical maximum rate at which a black hole can grow before the radiation from the infalling material pushes back against the incoming gas. Accreting near the Eddington limit means the black hole is feeding as fast as physics allows. There's no headroom. It's growing at maximum speed. That made sense given the timeline. If these black holes had to reach millions of solar masses within the first billion or 2 billion years of the universe, they didn't have time to grow slowly. They had to feed aggressively and continuously, pulling in as much gas as they could as fast as they could. The X-ray data confirmed that was happening. The black holes weren't dormant. They weren't growing in fits and starts. They were in the middle of a feeding frenzy, gorging themselves on the gas-rich environments of their young host galaxies and shining brightly in X-rays as a result. One object, the one designated 3 JWST Aegis 12014, became a case study for how multi-wavelength observations could piece together the full story. Webb's imaging showed it was compact and red. NESPIC's spectrum showed broad emission lines, indicating a black hole with gas moving at several thousand kilometers per second. Chandra's X-ray detection confirmed the black hole was accreting and emitting high-energy photons. The X-ray luminosity combined with the black hole mass estimated from the spectrum suggested an accretion rate near the Eddington limit. The redness suggested heavy dust obscuration. Putting all those pieces together, the picture that emerged was of a supermassive black hole, weighing a few million times the mass of the Sun, buried inside a dusty galaxy, feeding as fast as physics allowed, and shining so brightly in the infrared that Webb could detect it across more than 12 billion light-years of space. That's not a galaxy, that's a factory. A black hole factory, assembling one of the universe's most extreme objects in record time while hidden from view. The realization that so many little red dots had X-ray counterparts also forced a recalibration of how astronomers thought about obscured AGN in the early universe. Before Webb, obscured AGN at high redshift were thought to be rare. Most of the known high redshift AGN were bright quasars, unobscured systems that showed up in optical surveys. The assumption was that obscured AGN existed, but they were hard to find and probably not very common. Webb and Chandra together showed that assumption was wrong. Obscured AGN weren't rare. They were everywhere. Scattered across every deep field Webb observed, buried under layers of dust, feeding and growing and emitting X-rays just barely strong enough to be detected if you looked hard enough. They weren't the exception. They were a major component of the early AGN population, possibly even the dominant component if you counted all the systems too obscured to show up in X-rays. That shift in understanding had consequences for models of black hole growth. If obscured accretion was common in the early universe, it meant black holes spent a significant fraction of their early lives hidden from view. They weren't born as bright quasars. They started out buried, feeding quietly or not so quietly inside dusty cocoons, growing steadily until they became powerful enough to blow the dust away and emerge as visible quasars. The little red dots were a snapshot of that buried phase. They were the larval stage, the hidden growth period before the chrysalis broke open and the quasar emerged. And because Webb could see them, for the first time astronomers had a direct look at what was happening during that critical phase of black hole evolution. The X-ray detections weren't perfect. Many little red dots didn't have X-ray counterparts, either because they were too faint, too obscured, or simply hadn't been observed deeply enough in X-rays yet. Follow-up campaigns were already being planned to target more of them with Chandra and XMM Newton, staring at the same fields for longer stretches to push the detection limits deeper. But even with the incomplete data, the trend was clear. The little red dots were hiding black holes. The black holes were feeding. And the obscuration, the thick walls of gas and dust surrounding them, was both hiding them from optical view and explaining why they glowed so brightly in the infrared. The dust wasn't an obstruction, it was a signature. It told you exactly where to look if you wanted to find black holes in the act of growing. There was something almost poetic about the fact that the same dust that hid the black holes also revealed them. Without the dust, the little red dots would have been blue. They would have looked like ordinary quasars, bright in the optical and ultraviolet, and they probably would have been detected decades ago by Hubble or ground-based surveys. But because they were buried, because the dust absorbed the shorter wavelengths and re-radiated the energy in the infrared, they remained invisible until Webb came along with its gold-coated mirror and its ability to see at wavelengths Hubble couldn't touch. The obscuration that hid them from earlier telescopes was the very thing that made them stand out to Webb. And once Webb found them, the X-rays confirmed what the dust was hiding. Monsters. Feeding, growing, building themselves into the supermassive black holes that would one day sit at the centers of galaxies like the Milky Way, like M87, like every massive galaxy in the universe today. The X-ray data tied the story together, but it also opened the door to the next question. If the little red dots were obscured AGN, growing black holes buried inside dusty cocoons, where did those black holes come from in the first place? The standard model said they grew from stellar mass seeds, the remnants of the first massive stars, but the timescales were tight. Too tight, some researchers argued. To reach millions of solar masses in less than 1 billion years starting from a stellar mass seed required continuous feeding at or near the Eddington limit with no interruptions. That was possible, but it was also right at the edge of what the physics allowed, and the sheer number of little red dots scattered across the sky made it worse. If there were thousands of these systems in the early universe, the universe had to be producing stellar mass black hole seeds by the truckload and feeding them all continuously for hundreds of millions of years. That wasn't impossible, but it strained the model. The alternative was that the seeds weren't stellar mass. Maybe they were bigger, much bigger. Maybe some black holes in the early universe didn't form from collapsing stars at all. Maybe they formed directly from collapsing gas clouds, skipping the stellar phase entirely and starting out at tens of thousands or even hundreds of thousands of solar masses right from the beginning. That idea, called direct collapse, was exotic and unproven, but it solved the growth problem. Start with a massive seed, and you had plenty of time to reach supermassive status without pushing the accretion rate to its absolute limit. The little red dots couldn't tell you directly whether their black holes had grown from stellar seeds or formed through direct collapse. But the fact that they existed, that they were numerous, and that they were already massive so early in the universe's history made the direct collapse idea start looking less exotic and more necessary. Because if the black holes hadn't started big, it was hard to explain how they got so big so fast. And that's where the story turned from what we were seeing to what we thought might have happened long before Webb or Hubble or any telescope ever built could see anything at all. There's a problem with the standard story. Not a small problem, not the kind you can patch with a footnote or a revised parameter in a simulation, a foundational problem. The kind that makes you go back and check whether the entire framework you've been using for decades might be missing something important. And the problem is time, or more specifically, the lack of it. Black holes are supposed to grow slowly. That's what the models say. You start with a massive star, something weighing at least 20 or 30 times the mass of the Sun. The star burns through its fuel in a few million years, much faster than a smaller star like our Sun, and when it runs out of hydrogen to fuse, it can't support itself anymore. The core collapses. If the star is massive enough, the collapse doesn't stop at a neutron star. It keeps going, compressing the core down past the point where even neutron degeneracy pressure can hold it up, and the result is a black hole, a stellar mass black hole, weighing maybe 10 to 100 times the mass of the Sun. That's the starting point. That's the seed. From there, the black hole grows. It pulls in gas from its surroundings, maybe from a companion star if it's in a binary system, or from clouds of interstellar gas drifting nearby. The gas spirals inward, heats up, and crosses the event horizon. The black hole gains mass. Over time, if the gas supply is steady, the black hole can double its mass every few tens of millions of years. That's the Eddington limited growth rate, the maximum speed at which a black hole can accrete matter before the radiation from the infalling gas becomes so intense that it pushes back against the incoming material and chokes off the supply. Eddington limited growth is fast by human standards, but by cosmic standards it's a crawl. Run the numbers and the problem becomes obvious. A stellar mass black hole, weighing 100 solar masses, growing at the Eddington limit without interruption, takes about 1 billion years to reach 1 million solar masses. That's a long time. And to reach 1 billion solar masses, the kind of mass you see in the supermassive black holes sitting at the centers of massive galaxies today, you need several billion years, more than several, actually. You need time. Lots of it. And the early universe didn't have lots of it. The little red dots were sitting at redshifts where the universe was less than 1 billion years old. Some were even younger, appearing at epochs when the cosmos was only 600 million years old, barely 5% of its current age. And they were hosting black holes weighing millions of solar masses. In some cases, the black hole masses were estimated at 10 million solar masses or more. Those numbers don't fit the timeline. If you start with a stellar mass seed and grow at the Eddington limit, you can't get to 10 million solar masses in 600 million years. The math doesn't work. You're off by at least a factor of 10, maybe more. Either the black holes were growing much faster than the Eddington limit, which violates the physics of radiation pressure, or they didn't start as stellar mass seeds. They started bigger. Much bigger. That's where the idea of direct collapse comes in. Direct collapse black holes, or DCBHs, are hypothetical objects that skip the stellar phase entirely. Instead of forming from the death of a massive star, they form directly from the collapse of a giant cloud of primordial gas. No star, no supernova, just gas, collapsing under its own gravity, falling inward until it crosses the threshold where nothing can stop it, and a black hole forms in one swift, catastrophic event. If direct collapse happened in the early universe, the resulting black holes would be born heavy. Not 10 or 100 solar masses, thousands, tens of thousands, maybe even hundreds of thousands of solar masses right out of the gate. Start with a seed that size and the growth problem disappears. You've got a massive head start. Reaching 1 million solar masses or more within the first billion years becomes not just possible but almost inevitable. Direct collapse isn't a new idea. The concept has been around since at least the 1970s, when theorists first started modeling what would happen if a very large gas cloud collapsed without fragmenting into stars. Fragmentation is the usual outcome. When a cloud of gas starts to collapse, it doesn't fall inward as a single uniform blob. It breaks apart into smaller clumps. Those clumps collapse further and break apart again. Eventually, the clumps get dense enough and hot enough to ignite nuclear fusion, and stars are born. Dozens of stars, sometimes hundreds, all formed from the same original cloud. That's how star formation works. Fragmentation is the rule, not the exception. But fragmentation isn't inevitable. It requires cooling. When a gas cloud collapses, gravitational energy gets converted into heat. The gas heats up. If the gas can radiate that heat away, it cools down and the pressure drops. Lower pressure means less resistance to further collapse, so the cloud keeps shrinking. Eventually, it becomes so dense that it fragments into smaller pieces. But if the gas can't cool efficiently, if there's no way for it to radiate the heat away, the pressure stays high. High pressure resists further collapse. The cloud stays intact. It doesn't fragment. And if the cloud is massive enough and dense enough, it can collapse all the way down to a black hole without ever forming stars. The key to preventing cooling is chemistry, or more precisely, the lack of it. In the present-day universe, interstellar gas is filled with trace amounts of heavy elements: carbon, oxygen, nitrogen, silicon, iron. These elements were forged inside stars and scattered into space when those stars died. They're present in tiny quantities, usually less than 1% of the total mass of the gas, but they have an outsized effect on cooling. Heavy elements are very good at radiating energy. They absorb heat and re-emit it as infrared light, which escapes into space. That radiation carries energy away from the gas, allowing it to cool. Once the gas cools, it can collapse further, fragment, and form stars. But the early universe didn't have heavy elements, not in the first few 100 million years. The only elements present in significant quantities were hydrogen and helium, the products of the Big Bang itself. Hydrogen and helium are terrible at cooling. Atomic hydrogen can radiate, but only if it's ionized and then recombines, and even then it's not very efficient. Helium is even worse. It barely radiates at all under most conditions. The one molecule that does radiate efficiently in a primordial gas cloud is molecular hydrogen, H2, two hydrogen atoms bonded together. Molecular hydrogen can absorb vibrational energy and re-emit it as infrared photons, cooling the gas. In most early gas clouds, molecular hydrogen forms naturally, and once it does, the cloud cools, fragments, and forms stars, but not always. If the gas cloud is sitting in a strong radiation field, the kind produced by nearby massive stars or an early galaxy, that radiation can dissociate molecular hydrogen, breaking the bonds and turning H2 back into atomic hydrogen. No molecular hydrogen means no efficient cooling. No cooling means no fragmentation. And if the cloud is massive enough, it collapses anyway, heating up as it falls inward, but unable to radiate that heat away. The pressure builds, but gravity wins. The cloud keeps falling, faster and faster, denser and denser, until it crosses the point of no return and a black hole forms. Not a small black hole, a massive one, a direct collapse black hole. The conditions required for this to happen are very specific. You need a large reservoir of primordial gas, ideally several tens of thousands or even hundreds of thousands of solar masses worth. You need a strong radiation field to suppress molecular hydrogen formation, but not so strong that it ionizes all the hydrogen and blows the gas away entirely. And you need the collapse to happen fast, before stars have a chance to form and disrupt the process. If even a few massive stars ignite inside the collapsing cloud, their radiation and stellar winds can blow the gas apart, stopping the collapse before a black hole can form. The window is narrow, the conditions are precise, but if everything lines up just right, direct collapse can happen. And when it does, the result is a black hole that's born heavy, ready to start growing immediately without needing to spend hundreds of millions of years climbing up from a stellar mass seed. There's no direct observational evidence that direct collapse black holes exist. We've never seen one form. We can't. The process would have happened in the first few 100 million years after the Big Bang, an era that was almost entirely invisible to telescopes until Webb came along. But the little red dots are making the idea look less speculative and more necessary. Because if you're going to explain how black holes weighing millions of solar masses ended up in galaxies when the universe was less than 1 billion years old, you need a way to give those black holes a head start. Direct collapse provides that head start. It's one of the only mechanisms that does. One of the surprising aspects of the little red dots is just how many of them there are. By 2025, astronomers had catalogued over 300 of these objects across various Webb surveys. 300 is not a small number. It's not a handful of rare flukes sitting in unusual environments where everything happened to line up perfectly. It's a population, and populations need explanations. If 300 little red dots are hosting black holes that are too massive to have grown from stellar seeds in the available time, and if direct collapse is the only plausible way to produce massive seeds quickly, then direct collapse must have been common in the early universe. Not rare, not restricted to a few special regions, common enough that it happened hundreds of times in the small patches of sky Webb has surveyed so far, which means it must have happened thousands or tens of thousands of times across the entire observable universe. That realization has forced theorists to reconsider how often the conditions for direct collapse could actually occur. Earlier models assumed it would be rare because the requirements were so specific. You needed a primordial gas cloud, a strong radiation field to suppress cooling, and no nearby star formation to disrupt the collapse. The probability of all three conditions aligning was thought to be low, which meant direct collapse black holes, if they existed at all, should be uncommon. But the little red dots suggest the opposite. Either the conditions for direct collapse were more common than anyone expected, or there's another pathway to forming massive black hole seeds that we haven't thought of yet. One possibility is that the early universe was simply more conducive to direct collapse than the present-day universe. The gas was pristine, no heavy elements, no dust, no molecules except for molecular hydrogen, and even that could be easily suppressed by nearby radiation. The first galaxies were small and densely packed, meaning radiation fields from one galaxy could easily spill over and affect gas clouds in neighboring regions. And the overall density of the universe was higher, so gas clouds were more massive and more prone to collapse. Put all those factors together, and direct collapse might not have been rare at all. It might have been routine, a natural consequence of the environment. Another possibility is that direct collapse wasn't the only game in town. Some researchers have proposed that very massive stars, sometimes called supermassive stars, could have formed in the early universe and collapsed directly into intermediate mass black holes, weighing thousands of solar masses. Supermassive stars are different from the massive stars we see today. They're much bigger, potentially hundreds or even thousands of times the mass of the Sun, and they don't live very long. They burn through their fuel in just a few 100,000 years and then collapse. If they're massive enough, the collapse could produce a black hole weighing thousands of solar masses in one go. That's not as massive as a direct collapse black hole, but it's still a much better starting point than a stellar mass seed. And supermassive stars might have formed more easily in the early universe because the gas was so pristine. Without heavy elements to cool the gas efficiently, collapsing clouds could accumulate much more mass before igniting fusion, leading to stars far more massive than anything that forms today. Both direct collapse and supermassive star collapse are exotic scenarios. Neither one has been directly observed. But they're being taken seriously because the alternative, growing from stellar mass seeds at the Eddington limit, simply doesn't explain the data. The little red dots are there, they're real. Webb's imaging found them. NIII spectra confirmed they host accreting black holes. The X-ray detections proved those black holes are feeding, and the redshifts place them at epochs where conventional growth models can't produce black holes that massive. Something else had to happen. Either the seeds were bigger, or the growth was faster, or both. One of the more intriguing pieces of evidence supporting the massive seed hypothesis came from spectroscopic studies of individual little red dots. In June 2024, a team from Penn State published a paper in the astrophysical journal Letters describing detailed observations of 3 little red dots using NISPEC. The spectra showed something unexpected, not just the broad emission lines that indicated black hole accretion, but also features consistent with very old stars. Stars that were hundreds of millions of years old, sitting in galaxies that were themselves only 600 to 800 million years after the Big Bang. That shouldn't be possible. If a galaxy is only 600 million years old, the oldest stars in it should also be 600 million years old. You can't have stars older than the galaxy they're sitting in unless the stars formed earlier, much earlier. If some stars formed in the first 100 or 200 million years after the Big Bang and then got swept up into a larger galaxy later on, the galaxy could be young while the stars inside it were old. That scenario requires very early star formation, which in turn requires very early structure formation. And if structures were forming early enough to produce old stars by 600 million years, they were also forming early enough to produce massive gas clouds that could collapse into direct collapse black holes. The presence of old stars in the little red dots didn't prove direct collapse happened, but it supported the idea that the early universe was more active and more structured than the standard models predicted. Another surprising finding from the Penn State study was the sheer amount of mass involved. The black holes in the 3 objects they studied weren't just massive, they were enormous compared to the galaxies around them. In the present-day universe, the ratio of black hole mass to galaxy mass is fairly consistent. The black hole typically weighs about 0.1% of the total stellar mass of the galaxy. It's a small fraction, but it's predictable. In the little red dots, the ratios were inverted. The black holes were sometimes as massive as the entire stellar population of the galaxy, or even more massive. That's not how things are supposed to work. Galaxies grow, black holes grow, but they're supposed to grow together, more or less in lockstep, maintaining a rough balance. The little red dots looked unbalanced, as if the black holes had gotten a massive head start and the galaxies were still trying to catch up. That imbalance is exactly what you'd expect if the black holes formed through direct collapse. A direct collapse black hole could weigh 100,000 solar masses or more right from the start, while the galaxy around it might only have a few million solar masses worth of stars. The black hole would dominate the system, at least initially. Over time, the galaxy would grow through star formation and mergers, catching up to the black hole. Eventually, the ratio would normalize, settling into the relationship we see in galaxies today. But in the early stages, right after the black hole formed, the system would look lopsided, black hole heavy, galaxy light. That's what the little red dots looked like. The CERN Courier summary of the observations noted that some of the spectral features in the little red dots couldn't be produced by anything resembling a stellar population we have observed before. Specifically, they mentioned extreme Balmer breaks, sharp drops in the spectrum at the wavelength where hydrogen transitions from ionized to neutral. Balmer breaks are common in galaxy spectra. They tell you about the temperature and age of the stars, but the breaks seen in some little red dots were far more extreme than normal. The interpretation was that the light wasn't coming primarily from stars at all. It was coming from the black hole, or more precisely from the gas surrounding the black hole. The black hole's radiation was ionizing the gas, heating it to high temperatures, and the gas was re-emitting that energy in a way that produced an unusually strong Balmer break. That scenario only works if the black hole is very luminous and the gas around it is very dense. Both conditions fit the direct collapse picture. One of the challenges in proving the direct collapse hypothesis is that the process would have happened so early that we can't observe it directly. Even Webb, with all its infrared sensitivity, can't see back far enough to catch a direct collapse black hole in the act of forming. By the time Webb sees these objects, they've already formed and started growing. They're a few 100 million years old at minimum. The actual collapse event, the moment when the gas cloud reached critical density and fell inward to form a black hole, happened earlier in the truly dark ages of the universe, before any galaxies were bright enough to detect. We're seeing the aftermath, not the event itself. But the aftermath tells you a lot. If direct collapse happened, the resulting black holes should have certain properties. They should be massive, much more massive than stellar mass black holes. They should be feeding, because they'd be sitting in the middle of gas-rich environments where accretion is easy. And they should be surrounded by dense cocoons of gas, because the same conditions that allowed direct collapse, pristine gas without efficient cooling, would leave a lot of leftover gas around the black hole after it formed. That gas would obscure the black hole, absorbing its ultraviolet and optical light and re-radiating it in the infrared. The result would be a compact, red, highly luminous object, exactly what the little red dots look like. The dense gas cocoon idea has gained traction as one of the leading explanations for why the little red dots are so red. It's not just dust, it's gas. Thick, dense, primordial gas surrounding the black hole and blocking most of the shorter wavelength light. The gas is being ionized by the black hole's radiation, which heats it to high temperatures and causes it to glow in the infrared. The glow is bright enough to outshine the entire galaxy. And because the gas is so dense, it absorbs the optical and ultraviolet light almost completely, leaving only the infrared emission visible from the outside. That's why Webb sees them and Hubble didn't. Hubble was looking at the wrong wavelength. Webb is looking at exactly the right ones. If this interpretation is correct, the little red dots are snapshots of a very early phase of black hole growth. The black holes have just formed, or formed relatively recently, and they're still surrounded by the primordial gas clouds they collapsed from. The gas is feeding them, allowing them to grow rapidly, but it's also hiding them, obscuring the central engine and making them look red. Over time, the black holes will blow the gas away. The radiation pressure from their accretion disks will push the gas outward, clearing the cocoon and exposing the black hole to direct view. At that point, they'll stop being little red dots and start looking like quasars, bright and blue and visible across the electromagnetic spectrum. The little red dots aren't a permanent state, they're a phase. a transitional stage between the formation of the black hole and its emergence as a fully visible quasar. That timeline fits the broader picture of how supermassive black holes are thought to evolve: formation, obscured growth, emergence. The little red dots are being caught in the middle phase, the obscured growth phase, before the dust and gas have cleared. And if direct collapse is the formation mechanism, it explains how the black holes got so massive so fast. They didn't grow from small seeds, they were born big. One of the more unsettling implications of the direct collapse hypothesis is that it forces a rethinking of how common massive black hole seeds were in the early universe. If every little red dot started with a direct collapse black hole, and if there are hundreds of little red dots in the patches of sky Webb has surveyed, then the early universe must have been full of massive black hole seeds. Not just a few scattered here and there in special regions, but thousands or tens of thousands of them distributed throughout the cosmos. And if that's true, then the present-day population of supermassive black holes, the ones weighing millions and billions of solar masses that sit at the centers of galaxies today, might have almost all descended from direct collapse seeds. Stellar mass seeds might be the exception, not the rule. That's a radical shift from the standard picture. For decades, the assumption was that most supermassive black holes grew from stellar mass seeds, and that direct collapse, if it happened at all, was rare. The little red dots are flipping that assumption. They're suggesting direct collapse was common, maybe even dominant, and that the early universe was producing massive black hole seeds on an industrial scale. If that's right, then every quasar we see, every supermassive black hole sitting at the center of a massive galaxy, might trace its lineage back to a direct collapse event in the first few 100 million years after the Big Bang. The seeds were planted early, they grew fast, and by the time the universe was a few billion years old, they'd become the monsters we see today. The direct collapse idea also has implications for the broader question of how galaxies and black holes co-evolve. The fact that almost every massive galaxy has a supermassive black hole at its center suggests a deep connection between the two. Galaxies don't just happen to have black holes. The black holes seem to play a role in regulating the galaxy's growth, shutting down star formation once the black hole becomes powerful enough to blow gas out of the galaxy entirely. But how did that relationship get established? If black holes formed first, through direct collapse, and galaxies formed around them later, then black holes were drivers of galaxy evolution from the very beginning. They weren't passengers, they were architects. The little red dots, with their massive black holes and small galaxies, might be showing us the moment when that relationship was being established, when the black hole was already in place and the galaxy was just starting to catch up. Not everyone is convinced. The direct collapse hypothesis is still debated. Some researchers argue that the observed properties of the little red dots can be explained with conventional growth models if you assume the black holes were feeding faster than the Eddington limit, a scenario called super-Eddington accretion. Super-Eddington accretion is theoretically possible if the geometry of the accretion flow is just right. Instead of a thin disk where radiation pressure pushes outward uniformly, you could have a thick, puffy flow where radiation escapes in certain directions while gas continues to fall in from others. That would allow the black hole to grow faster than the standard Eddington limit without violating the physics of radiation pressure. If super-Eddington accretion was common in the early universe, maybe stellar mass seeds could grow fast enough to explain the little red dots after all. But even if super-Eddington accretion was happening, it doesn't fully solve the timeline problem. You still need stellar mass seeds to form early enough that they have time to grow. And you still need to explain why there are so many massive black holes in the early universe. Direct collapse provides a cleaner explanation. It gives you massive seeds early without requiring any exotic accretion physics. The black holes start big, they grow at normal rates, and by the time Webb sees them, they're already massive enough to dominate their host galaxies. The debate will continue until someone finds definitive evidence one way or the other. Ideally, that evidence would be a direct observation of a black hole forming through direct collapse, but that's not going to happen anytime soon. The next best thing would be to find a little red dot with properties that can only be explained by a massive seed. A black hole so massive at such an early epoch that no plausible growth model starting from a stellar mass seed could produce it. If such an object exists, Webb might find it. The telescope is still observing. The surveys are still running. And every new deep field brings more little red dots into view. One of them might be the smoking gun. For now, the direct collapse hypothesis remains exactly that, a hypothesis. But it's a hypothesis that's gaining traction because it explains the data better than the alternatives. The little red dots are there, they're numerous, they're massive, and they're young. Something had to produce them. Either the universe found a way to grow black holes much faster than we thought possible, or it found a way to start with bigger seeds. Direct collapse is the simplest way to start with bigger seeds. And if the little red dots really are the descendants of direct collapse black holes, then we're seeing the birth of a new generation of cosmic monsters. Seeds that would grow over billions of years into the supermassive black holes we see today, the ones weighing billions of solar masses, the ones sitting at the centers of galaxies like silent gods, pulling matter inward and shaping the evolution of everything around them. The little red dots aren't just distant galaxies with unusually bright cores, they're the origin story. The moment when the monsters were born, before they grew large enough to swallow stars, before they became the engines of quasars, before they became the architects of galaxies, they were seeds, massive seeds, and the universe was about to watch them grow. There's a photograph that circulates among astronomers, not an image really, more of a visualization. A comparison. On the left side, you see a tiny red dot, barely more than a pixel in a Webb infrared image. Compact, faint, easy to miss if you didn't know where to look. On the right side, you see a black hole, not just any black hole, TON 618, 66 billion times the mass of our Sun. An event horizon so large that light, the fastest thing in the universe, would take 2 weeks to cross from one side to the other. A monster so massive that the entire solar system, Sun to Pluto and far beyond, could fit comfortably inside the radius of its event horizon with room to spare. 2 images, one object at the beginning of its life, one at the end. And the space between them is the story of how the universe builds its most extreme objects. TON 618 is not a black hole you can visit. It's not even a black hole you can see. What we observe when we point a telescope at TON 618 is a quasar, the brilliant glow of matter falling into the black hole at velocities approaching the speed of light, heating to millions of degrees and shining so brightly that it outshines entire galaxies. The quasar sits more than 10 billion light-years away, meaning the light reaching us today left that system when the universe was less than 4 billion years old. We're not seeing TON 618 as it exists now. We're seeing it as it existed in the early universe, already grown to monstrous size, already feeding, already shining with the luminosity of 140 trillion suns. And the question that keeps astronomers awake at night is simple. How did it get that big that fast? The little red dots might be the answer. Or more precisely, objects like the little red dots. The compact, red, heavily obscured black holes Webb has been finding scattered across the early universe at redshifts where the cosmos was only a few 100 million to 1 billion years old. If those objects are the seeds, and if they grew over the next several billion years through a combination of steady accretion and violent mergers, then by the time the universe was 3 or 4 billion years old, some of them could have reached the scale of ton 618. Not all of them. Most black holes don't grow that large. But a few, sitting in the right environments with the right gas supplies and the right merger histories could. And ton 618 is what happens when everything goes right, or wrong, depending on your perspective. Let's start with the scale, because the scale is the whole problem. 66 billion solar masses. Some recent estimates have revised that number slightly downward, closer to 40 billion. But either figure places ton 618 in a category of its own. Astronomers call it ultramassive. There's no formal threshold for when a black hole becomes ultramassive rather than just supermassive, but anything above 10 billion solar masses generally gets the title. Ton 618 is 6 times heavier than that. It's one of the most massive black holes ever confirmed, and it sits at the extreme tail end of the black hole mass distribution. Most supermassive black holes weigh a few million to a few 100 million solar masses. Ton 618 weighs more than 100 times that. It's not just big, it's an outlier, a statistical anomaly, the kind of object that shouldn't exist unless the universe found a way to build it that we don't fully understand. The accretion disk around ton 618 extends for light weeks in every direction. Light weeks, the distance light travels in 7 days. Compare that to the solar system. Light from the sun takes about 8 minutes to reach Earth. It takes about 5.5 hours to reach Pluto. The accretion disk of ton 618 dwarfs that entire span. Gas spiraling into the black hole at that distance is still moving at thousands of kilometers per second, accelerated by the immense gravity of the central object. As the gas falls inward, friction heats it to temperatures of millions of degrees. At those temperatures, the gas glows. Ultraviolet, optical, infrared, X-rays. The entire electromagnetic spectrum lights up. The total luminosity of the quasar, the combined output of all that glowing gas, is roughly 140 trillion times the luminosity of the sun. Put another way, ton 618 is brighter than 100,000 Milky Way galaxies combined. One object, brighter than 100,000 galaxies. That's the kind of power you get when you drop matter into a black hole weighing 66 billion suns. The brightness is how we found ton 618 in the first place. It was catalogued back in 1957 during a photographic survey at the Tonantzintla Observatory in Mexico. At the time, nobody knew what it was. It looked like a faint blue star. 15 years later, improved instruments revealed it wasn't a star at all. It was a quasar, a galaxy core so bright that it outshone every star in the galaxy around it. Redshift measurements placed it at a distance of about 10.4 billion light-years, and by the early 2000s, observations of the quasar's spectrum and variability allowed astronomers to estimate the mass of the central black hole. The answer came back in the tens of billions of solar masses. It's been refined since then, but the conclusion hasn't changed. ton 618 is hosting one of the most massive black holes known to science, and it was already that massive when the universe was less than 4 billion years old. That timeline is the crux of the problem. 4 billion years sounds like a long time. It's not. Not when you're trying to grow a black hole from a small seed to 66 billion solar masses. Run the math, and the problem becomes obvious. Start with a stellar mass black hole. say 100 solar masses, the kind you'd get from the collapse of a massive star. Grow it at the Eddington limit, the maximum rate at which a black hole can accrete matter before the radiation from the infalling gas pushes back and chokes off the supply. Even at that rate, it takes about 1 billion years to grow from 100 solar masses to 1 million, another billion to reach 100 million, another billion to reach 10 billion. You're running out of time. 4 billion years isn't enough to grow a 66 billion solar mass black hole starting from a stellar mass seed, not even close. You need a different starting point, a bigger seed, or a faster growth rate. Or both. That's where the little red dots come in. If the little red dots are direct collapse black holes, or the descendants of supermassive stars, they could have started out weighing tens of thousands or even hundreds of thousands of solar masses. That's a massive head start. From there, growing to 1 million solar masses takes a few 100 million years instead of 1 billion. Growing to 10 million takes maybe 500 million. Growing to 1 billion takes a few billion. The timeline starts to work. You can reach TON 618 scale in 4 billion years if you start with a seed that's already 100,000 solar masses, and if you keep feeding it steadily at or near the Eddington limit with no major interruptions. It's tight. It's right at the edge of what the physics allows, but it's possible. The little red dots observed by Webb aren't as massive as TON 618. Not yet. The black hole mass estimates for the little red dots, based on the widths of their broad emission lines and the luminosities of their accretion disks, come in at a few million to a few tens of millions of solar masses. That's still huge for objects being observed when the universe was less than 1 billion years old. But it's not ultramassive. Not yet. The little red dots are juveniles. They're massive black holes in the process of growing, surrounded by dense cocoons of gas and dust, feeding rapidly and shining brightly in the infrared. They're not finished. They're just getting started. And if you follow their growth forward in time, tracing what happens over the next several billion years, you start to see how an object like TON 618 could emerge. The growth process isn't simple. Black holes don't just sit still and accrete gas at a steady rate for billions of years. The environment changes. Gas gets consumed, star formation heats and ionizes the surrounding material, making it harder for the black hole to pull in more gas. Supernova explosions blow gas out of the galaxy entirely. The black hole's own radiation pushes gas away, temporarily shutting off the accretion until more gas can fall back in. Growth happens in bursts, periods of rapid feeding followed by quieter periods when the gas supply dries up. Over billions of years, those bursts add up. The black hole gains mass, slowly at first, then faster as the galaxy grows and merges with other galaxies, each merger delivering a fresh supply of gas and, sometimes, another black hole. Galaxy mergers are critical. When two galaxies collide, their gas clouds slam into each other, lose angular momentum, and fall toward the centers of the galaxies. That gas feeds the black holes. If both galaxies have central black holes, and if the galaxies merge completely, the two black holes will eventually spiral inward and merge as well. Black hole mergers are violent events. They release enormous amounts of energy in the form of gravitational waves, ripples in space-time itself. But they also produce a single larger black hole. Merge a 1 million solar mass black hole with another 1 million solar mass black hole, and you get a 2 million solar mass black hole. Repeat that process a few times, and the mass starts climbing quickly. A black hole that starts out weighing 100,000 solar masses could reach 1 billion solar masses in a few billion years through a combination of steady accretion and a handful of major mergers. Keep going for another billion years and you could reach 10 billion. Push the timeline to 4 billion years, stack a few more mergers on top, and 66 billion starts looking less impossible. The environment matters too. Not every galaxy is equally good at feeding its central black hole. The rate of gas inflow depends on how much gas is available, how efficiently the galaxy can funnel that gas toward the center, and how much of that gas actually makes it to the black hole instead of getting blown away by stellar winds or used up in star formation. In the early universe, galaxies were smaller and denser, gas fractions were higher. A higher fraction of the galaxy's total mass was in the form of gas rather than stars, which meant more fuel for both star formation and black hole growth. The early universe was also more chaotic. Galaxies collided more often because they were closer together and hadn't had time to spread out as much as they have today. More collisions meant more mergers. More mergers meant more black hole growth. The environment in the first few billion years after the Big Bang was, in many ways, optimized for building massive black holes quickly. TON 618 probably benefited from all of those factors. It likely started as a massive seed, possibly a direct collapse black hole, or the remnant of a supermassive star sitting at the center of a gas-rich galaxy in the early universe. That seed fed steadily for hundreds of millions of years, growing at or near the Eddington limit. The galaxy merged with other galaxies, each merger delivering more gas and, in some cases, another black hole. The black holes merged. The mass climbed. By the time the universe was 3 or 4 billion years old, the black hole had reached tens of billions of solar masses. It was still feeding. The quasar phase, the period when the black hole is accreting so much gas that it shines as one of the brightest objects in the universe, was in full swing. That's what we're seeing when we observe TON 618. We're not seeing the black hole itself. We're seeing the light from the gas falling into it. The final moments before that gas crosses the event horizon and disappears forever. The connection between the little red dots and TON 618 isn't direct. We can't trace a single object from one phase to the other. The little red dots are being observed at redshifts of 7 or 8 or higher, meaning we're seeing them as they existed when the universe was less than 1 billion years old. TON 618 is being observed at a redshift of about 2.2, meaning we're seeing it when the universe was about 3.7 billion years old. That's a gap of nearly 3 billion years. In that time, the little red dots would have evolved. The dust cocoons would have been blown away by radiation pressure from the growing black holes. The galaxies around them would have grown through star formation and mergers. The black holes themselves would have grown through accretion and mergers. By the time they reached the epoch where we observed TON 618, they would look completely different. No longer compact red dots buried in dust. Now bright quasars shining across the entire electromagnetic spectrum. Naked black holes with clear views of their accretion disks, feeding at maximum rates, dominating their host galaxies. Not every little red dot would become a TON 618. Most wouldn't. TON 618 is an extreme case. It's sitting at the high end of the black hole mass distribution, which means it's rare. For every TON 618, there are hundreds of supermassive black holes weighing a few million or a few hundred million solar masses. Those are the typical ones, the ones sitting at the centers of normal galaxies. The little red dots, if they're the seed population, would grow into the full range of supermassive black holes we see today. Some would become modest black holes weighing a few million suns, like the one at the center of the Milky Way. Others would become more massive, reaching a few hundred million solar masses, like the black hole in the center of M87. A few, sitting in the most favorable environments with the richest gas supplies and the most violent merger histories, would keep growing. 10 billion solar masses, 20 billion, 50 billion, and in rare cases, 66 billion. TAON 618 is what happens when a little red dot wins the cosmic lottery. Everything goes right. The seed is massive, the gas supply is steady, the mergers keep coming, and by the time the universe is 4 billion years old, you've built a monster. The possibility that the little red dots represent the seed population is being discussed as one of the most important implications of Webb's discoveries. If confirmed, it would close a major gap in our understanding of black hole evolution. For decades, astronomers have known that supermassive black holes exist in the centers of almost all massive galaxies. They've also known that those black holes must have started small as seeds and grown over time. But the details of that growth process have been murky. How big were the seeds? How fast did they grow? What role did mergers play? What role did the surrounding galaxy play? The little red dots are providing answers to those questions. They're showing us what the seeds looked like. Compact, red, obscured, already massive by the time the universe was less than 1 billion years old. And they're showing us that the seeds were numerous, scattered across the sky in numbers that suggest direct collapse or supermassive star collapse was a common process in the early universe, not a rare fluke. The evolutionary link between the little red dots and objects like TON 618 is more than just speculation. It's supported by the timeline, the masses, and the environments. The little red dots are being observed at the right epoch to be the progenitors of the supermassive black holes we see a few billion years later. Their masses are in the right range to grow into TON 618 scale black holes if you allow for steady accretion and a few major mergers. And their environments, gas-rich galaxies in the early universe, are exactly the kinds of places where rapid black hole growth is expected. The pieces fit, the story holds together, the little red dots are the seeds. TON 618 is the tree. One of the striking aspects of TON 618 is that it's not alone. It's rare, yes, but it's not unique. There are other ultramassive black holes, not many, a few dozen confirmed cases, but enough to establish that TON 618 scale objects are a real population, not a one-off anomaly. That's important because it means the process that built TON 618, whatever it was, happened multiple times. The universe found a way to build ultramassive black holes in multiple locations, and it did so early enough that we can observe them when the universe was still relatively young. If the little red dots are the seeds, and if the growth process we've been describing is real, then every ultramassive black hole we see today should have started as something like a little red dot, a compact, obscured, rapidly accreting black hole sitting in a gas-rich galaxy in the first billion years after the Big Bang. Some of them grew into TON 618, others grew into slightly smaller monsters. But they all started the same way, as seeds. The accretion rates required to reach TON 618 scale are extreme. Even with a massive seed, you need to feed the black hole at or near the Eddington limit for billions of years. That's a sustained, relentless feeding rate with very little downtime. In practice, real black holes don't grow that smoothly. They go through phases. Active phases when gas is abundant and the accretion rate is high. Quiet phases when the gas runs out and the accretion slows or stops entirely. The duty cycle, the fraction of time the black hole spends in an active phase, is typically less than 100%, maybe 50%, maybe 30%. But TON 618 couldn't have grown to its current mass with a low duty cycle. It needed to spend most of its time feeding. That suggests its environment was unusually favorable. Lots of gas, frequent mergers, minimal disruptions from supernova-driven winds or other processes that might blow gas away. TON 618 lived in a cosmic sweet spot, a place where everything conspired to feed the black hole as fast as possible for as long as possible. The role of mergers in building ultramassive black holes can't be overstated. Accretion alone, even at the Eddington limit, has a hard time producing black holes weighing tens of billions of solar masses in just a few billion years. Mergers provide a shortcut. Instead of waiting for the black hole to slowly accrete gas, you add mass all at once by merging with another black hole. A black hole weighing a billion solar masses that merges with another black hole weighing a billion solar masses doubles its mass instantly. No accretion required. If TON 618 went through even a handful of major mergers during its growth, those mergers could have contributed significantly to its final mass, and in the dense, chaotic environment of the early universe, major mergers weren't rare, they were common. Galaxies collided all the time. Black holes merged all the time. It was a violent, active era. TON 618 grew up in that violence, and the violence fed it. There's another piece of the story that's often overlooked. The gas that feeds a black hole doesn't just appear out of nowhere, it has to come from somewhere. In the early universe, that gas came from the intergalactic medium, the diffuse web of gas filling the space between galaxies. As galaxies formed, they pulled in gas from their surroundings, building up reservoirs that could fuel both star formation and black hole growth. But not all galaxies were equally good at holding on to their gas. Smaller galaxies with weaker gravitational fields struggled to keep their gas from being blown away by stellar winds and supernova explosions. Larger galaxies with deeper gravitational wells could hold on to their gas more easily. TON 618 probably grew up in one of those larger galaxies, or in a galaxy that became larger through mergers. The deeper the gravitational well, the more gas the galaxy could hold, and the more gas available to feed the black hole. TON 618 didn't just get lucky with its seed mass and its merger history. It also got lucky with its environment. It sat in a galaxy that could supply it with gas for billions of years without interruption. The luminosity of TON 618 tells you how fast it's feeding right now. Or rather, how fast it was feeding 10.4 billion years ago, which is when the light we're observing today left the system. Quasar luminosity is directly tied to accretion rate. The more gas falling into the black hole per unit time, the brighter the quasar. TON 618's luminosity of 140 trillion solar luminosities suggests an accretion rate of several tens of solar masses per year. That's a staggering amount of matter. In a single year, TON 618 consumes tens of times the mass of our entire Sun. Every year, for millions of years. That kind of feeding rate is only sustainable if the gas supply is enormous and if the galaxy can keep funneling gas toward the center as fast as the black hole can eat it. The fact that TON 618 was shining that brightly when the universe was less than 4 billion years old tells you that its environment was still gas-rich at that epoch. The reservoir hadn't dried up yet. The black hole was still feeding, still growing, still on its way to becoming one of the most massive objects the universe would ever produce. The little red dots, by comparison, are feeding at lower rates. Their luminosities are a few orders of magnitude below TON 618. That's expected. They're smaller. Their black holes weigh a few million to a few tens of millions of solar masses, not tens of billions. Their accretion rates are correspondingly lower, but they're still feeding. They're still growing. And if you give them a few billion years to keep feeding, keep merging, keep pulling in gas from their surroundings, some of them will reach TON 618 scale. The little red dots are the beginning. TON 618 is the end, or closer to the end. Because even TON 618 isn't finished, it's still feeding, the quasar is still shining, the black hole is still growing. Eventually the gas will run out, the quasar will shut off. The black hole will become dormant, sitting quietly at the center of a massive elliptical galaxy, no longer accreting, no longer shining. But that phase comes later, much later. When we observe TON 618, we're seeing it in its prime, the peak of its activity, the moment when it's feeding as fast as it ever will. The connection between the little red dots and TON 618 is also a connection between two different observational techniques. The little red dots were found through infrared imaging and spectroscopy, using Webb's ability to detect faint red sources buried under layers of dust. TON 618 was found through optical surveys and later studied in detail using optical and X-ray observations. The two populations look completely different at first glance. One is red and compact and barely visible. The other is blue and bright and impossible to miss. But they're part of the same evolutionary sequence. The little red dots are the obscured phase. TON 618 is the unobscured phase. The dust cocoon has been blown away. The black hole is fully exposed. The galaxy around it is mature. The transition from one phase to the other happens over a few billion years, and we're lucky enough to have telescopes powerful enough to see both ends of the timeline. Webb shows us the seeds. Hubble and ground-based telescopes show us the giants. Put the two together, and you have the full story of how the universe builds its most extreme objects. One of the more unsettling realizations is that TON 618 is what a little red dot becomes if everything goes right. But most little red dots won't become TON 618. They'll become smaller black holes, more typical black holes. The kind weighing a few million or a few 100 million solar masses. Those are the ones sitting at the centers of normal galaxies today. The Milky Way's black hole, Sagittarius A star, weighs about 4 million solar masses. It probably started as a little red dot too, a compact, obscured, rapidly accreting black hole in a gas-rich galaxy in the early universe. Over billions of years, it grew through accretion and a few minor mergers. It never became TON 618. It never had to. 4 million solar masses is massive enough to dominate the center of the galaxy and shape the evolution of the stars around it. Not every black hole needs to become ultramassive to be important, but the fact that some do, the fact that the universe is capable of producing objects like TON 618, tells you something about how extreme the conditions in the early universe could be. The gas was there. The mergers were there, the seeds were there, and in a few rare cases, everything lined up perfectly, and the result was a monster. The little red dots are giving us the first direct look at the seed population. Before Webb, we had to infer the existence of seeds from the supermassive black holes we saw in the present-day universe. We knew they had to start somewhere, we just couldn't see where. Now we can. The little red dots are the where. They're the seeds, caught in the act of growing, buried under dust but shining brightly enough in the infrared that Webb can detect them across more than 12 billion light-years of space. And if the little red dots are the seeds, then every supermassive black hole we see today, from the modest ones like Sagittarius A star to the ultramassive ones like TON 618, traces its lineage back to an object that looked like a little red dot. A compact, red, heavily obscured source glowing faintly in the infrared in the first billion years after the Big Bang. That's the origin story. That's where the monsters come from. The evolutionary pathway from little red dot to TON 618 is now one of the central stories in black hole astronomy. It ties together observations from across the electromagnetic spectrum, infrared, optical, X-rays. It ties together objects from across cosmic time, the early universe, the middle universe, the present day, and it ties together theory and observation in a way that finally makes sense of how supermassive black holes grew so large so fast. The seeds were massive, the accretion was rapid, the mergers were frequent, and over a few billion years those seeds became giants. The little red dots are the proof. TOE 618 is the result. And the story connecting them is the story of how the universe builds its most powerful engines, one burst of accretion at a time, one merger at a time, 1 billion solar masses at a time, until the black hole is so massive that it dominates everything around it and becomes the brightest, most extreme object the cosmos can produce. The little red dots planted the seeds, the universe watered them, and TOE 618 is what grew. The little red dots are forcing a rewrite, not a revision, not a footnote in the next edition of the textbook. A complete, ground-up rewrite of the story astronomers have been telling for decades about how the universe assembled itself in the first billion years after the Big Bang. The story used to go like this. First, the universe cooled enough for hydrogen to form. Then, over hundreds of millions of years, that hydrogen clumped together under gravity and ignited the first stars. Those stars lived and died, enriching the surrounding gas with heavier elements. From that enriched gas, the first galaxies assembled slowly, piece by piece, over hundreds of millions of years. And somewhere in the middle of that process, black holes formed from the deaths of massive stars and began growing at the centers of those galaxies, feeding on gas and stars, and slowly accumulating mass. By the time the universe was a few billion years old, some of those black holes had grown large enough to be called supermassive, weighing millions or billions of times the mass of the Sun. The galaxies and their black holes grew together in lockstep, each shaping the evolution of the other. That was the story. Clean, linear, predictable. The little red dots do not fit that story. They're sitting at redshifts where the universe was only 600 to 800 million years old, barely 5% of its current age, and they're already hosting black holes weighing tens of thousands to millions of solar masses, not dormant black holes, not quiet black holes sitting in the background waiting for something to happen. Feeding black holes, accreting gas at rates close to or exceeding the Eddington limit, shining so brightly in the infrared that Webb can detect them across more than 12 billion light-years of space. And they're not rare. They're not scattered outliers, sitting in a handful of unusual environments. They're everywhere. Thousands of them, scattered across every deep field Webb has observed. A population, a common feature of the early universe, and common means important. Common means the universe was doing something in its first billion years that the standard models didn't account for. The discovery of the little red dots entered the scientific literature in March 2024, though the objects themselves had been showing up in Webb's data since the telescope's first deep observations in mid-2022. For the first year or so, they were a curiosity. Astronomers noticed them, catalogued them, ran preliminary analyses, but the full scope of what they represented didn't become clear until the spectroscopy started coming in. That's when the picture shifted. The spectra showed broad emission lines, the signature of gas moving at thousands of kilometers per second around a central black hole. They showed unusual features that couldn't be produced by any normal stellar population, and in some cases they showed signs of very old stars sitting in galaxies that were supposedly far too young to host stars that old. The data didn't just complicate the standard story, it broke it. And by early 2024, Enough data had accumulated that researchers couldn't ignore the implications anymore. The little red dots weren't just distant galaxies, they were something the models hadn't predicted. A phase of black hole growth that was supposed to be rare, if it existed at all, but was turning out to be common, possibly dominant. The paradigm shift is this. Black holes in the early universe may not have waited for galaxies to assemble before they started growing. They may have formed first, or at least very early, as massive seeds weighing tens of thousands or hundreds of thousands of solar masses, and they may have started feeding immediately, pulling in gas from their surroundings, and growing rapidly even while the galaxies around them were still in the process of forming. That inverts the old picture. In the old picture, galaxies came first, and black holes followed, growing slowly in the centers of those galaxies over billions of years. In the new picture, black holes and galaxies may have grown together from the very beginning, or black holes may have even led the way, forming first and then shaping the assembly of the galaxies around them. The little red dots are evidence for that new picture. They're showing us black holes that are already massive when the universe is less than 1 billion years old, sitting in galaxies that are still small and still forming stars. The black holes aren't keeping pace with the galaxies, they're ahead of them. That changes everything. If black holes formed early and grew fast, they would have had a much larger impact on the early universe than anyone realized. Black holes don't just sit passively at the centers of galaxies, they interact with their surroundings. When a black hole accretes gas, it heats that gas to millions of degrees and emits radiation across the entire electromagnetic spectrum. That radiation ionizes nearby gas, stripping electrons off atoms and preventing the gas from cooling down enough to form stars. If enough black holes were active in the early universe, their collective radiation could have contributed significantly to reionization, the process by which the universe transitioned from a neutral gas-filled state to the ionized state we see today. Reionization is one of the major milestones in cosmic history. It happened somewhere between 200 and 1 billion years after the Big Bang, and it fundamentally changed the properties of the intergalactic medium. Before reionization, the gas between galaxies was neutral and opaque to certain wavelengths of light. After reionization, that gas was ionized and transparent. Astronomers have traditionally assumed that reionization was driven mostly by stars, by the ultraviolet light from the first massive stars and the first galaxies. But if the little red dots are as common as they appear to be, black holes may have played a much larger role than anyone expected. They may have been major contributors to reionization, pumping high-energy photons into the intergalactic medium and ionizing vast regions of space. That's a different story, a messier story. One where black holes aren't just passengers in the evolution of galaxies but active drivers of cosmic history from the very beginning. The implications for baryonic matter distribution are equally significant. Baryonic matter is the ordinary stuff. Protons, neutrons, electrons, the matter that makes up stars, planets, gas, dust, and everything you can see or touch. In the present-day universe, most baryonic matter is locked up in stars or sits in the diffuse gas between galaxies. But in the early universe, the distribution was different. More of the baryonic matter was in the form of gas, and that gas was denser and more concentrated in the regions where galaxies were starting to form. Where that gas ended up, how quickly it was converted into stars, and how much of it was blown out of galaxies by stellar winds or black hole feedback. All of those factors shaped the evolution of the first galaxies. The little red dots suggest that a significant fraction of the baryonic matter in the early universe may have been tied up in or around actively feeding black holes, not stars, not diffuse gas clouds, black holes. or more precisely, the gas falling into black holes and the dense cocoons of gas and dust surrounding them. If that's true, then models of galaxy formation need to account for the fact that black holes were consuming and redistributing baryonic matter much earlier than previously thought. The black holes weren't just growing, they were pulling gas inward, heating it, ionizing it, and in some cases blowing it back out into space through powerful winds and jets. All of that activity would have affected how galaxies formed, how much gas was available for star formation, and how the first structures in the universe assembled. The fact that the little red dots are so numerous is one of the most unsettling aspects of the discovery. Before Webb, astronomers thought that massive black holes in the early universe were rare. The known population consisted mostly of bright quasars, a few dozen objects scattered across the sky at high redshift. Quasars were assumed to be the tip of the iceberg, the brightest and most active examples of an otherwise small population. The little red dots have flipped that assumption. They're not the tip of the iceberg. They're the iceberg. The quasars are just the few that happen to clear their dust cocoons and become visible in the optical. The little red dots are the majority, the ones still buried under gas and dust, feeding and growing, but hidden from view at shorter wavelengths. If there are thousands of little red dots in the small patches of sky Webb has surveyed so far, and if those patches are representative of the universe as a whole, then the total population of actively accreting black holes in the early universe must be enormous. Tens of thousands, hundreds of thousands, maybe more. That's not a rare population. That's a standard feature of the early cosmic landscape. And if black holes were that common, they weren't anomalies, they were a central part of how the universe evolved. The spectroscopic campaigns have revealed something else. The little red dots are not a uniform population, they're a mix. Some are dominated by black hole emission, with broad lines and high luminosities consistent with active galactic nuclei. Others show signs of intense star formation, with narrower lines and spectral features more consistent with dusty galaxies churning out new stars at a rapid rate. Still others show evidence of old stellar populations, stars that are hundreds of millions of years old sitting in galaxies that should only be a few 100 million years old themselves. That diversity suggests the little red dots aren't a single class of object. They're a snapshot of a range of evolutionary stages. Some are galaxies in the process of forming stars. Some are galaxies whose black holes have recently turned on and started dominating the light. Some are galaxies that have already gone through a burst of star formation and are now in a quieter phase. The common thread is that they're all compact, they're all red, and they're all sitting at epochs where the universe was still very young. They're pieces of a puzzle that's still being assembled, and the final picture is going to be more complicated than anyone expected. One of the largest spectroscopic samples came from a Webb campaign that observed about 300 little red dots and identified roughly 30 to 50 of them as the specific class of interest, actively accreting black holes with broad emission lines and compact sizes. That's a significant fraction. It's not all of them, which confirms that the population is mixed. But it's enough to establish that buried black holes are a common component of the early universe. And the fact that the campaign had to observe 300 objects to confirm 30 to 50 targets tells you something about the challenge of studying these objects. They're faint, they're distant, and they're buried under so much gas and dust that distinguishing black hole emission from starlight requires detailed spectroscopy and careful modeling. Imaging alone can't do it. You need spectra, and spectra take time. Webb's NIR spec instrument is powerful, but it can only observe so many objects at once, and each observation requires hours of exposure time to build up enough signal. The field is still in the early stages of characterizing the population. More observations are planned, more data are coming in, and every new spectrum adds another piece to the puzzle. The theoretical challenge is to figure out how the black holes got so massive so fast. The two leading ideas are direct collapse and supermassive star collapse. Direct collapse is the process where a giant cloud of primordial gas, weighing tens of thousands or hundreds of thousands of solar masses, collapses straight into a black hole without forming stars first. It requires very specific conditions. The gas has to be hot enough and dense enough to collapse quickly, but it can't cool down too fast, or it will fragment into stars instead of collapsing as a single object. The cooling has to be suppressed, usually by a strong radiation field from nearby stars or galaxies that dissociates molecular hydrogen and prevents the gas from radiating energy efficiently. If those conditions are met, the collapse happens fast. The cloud falls inward, reaches a critical density, and a black hole forms in one catastrophic event. The black hole is born massive, already weighing tens of thousands of solar masses, and it's sitting in a gas-rich environment where it can start accreting immediately. That gives it a huge head start. From there, growing to 1 million or 10 million solar masses in a few 100 million years is much easier than starting from a stellar mass seed of 100 solar masses. Supermassive star collapse is similar, but starts with a different object. Instead of a gas cloud collapsing directly into a black hole, a very massive star forms first. Not a normal massive star like the ones we see today, which weigh a few tens of times the mass of the Sun. A supermassive star, weighing hundreds or even thousands of solar masses. Stars that massive can only form in the pristine gas of the early universe, because they require gas that's metal-free and can't cool efficiently. If the gas cools, it fragments into smaller clumps and forms normal stars. But if the cooling is suppressed, the gas can accumulate into a single, very massive object. That object ignites fusion and becomes a star, but it doesn't live long. A supermassive star burns through its fuel in a few 100,000 years and then collapses. If it's massive enough, the collapse produces a black hole weighing thousands of solar masses right away. That's still a better starting point than a stellar mass seed, and it solves the growth problem in much the same way direct collapse does. Both scenarios require conditions that were common in the early universe but are rare today. The early universe was metal-free. There were no heavy elements to help the gas cool and fragment. The gas clouds were more massive because the overall density of the universe was higher, and the environment was more chaotic, with galaxies colliding and merging frequently, delivering fresh supplies of gas to the black holes. All of those factors made it easier for massive seeds to form, and easier for those seeds to grow rapidly once they did. The little red dots are the evidence that it happened. They're the result of that process. Massive seeds forming early, feeding on gas-rich environments, and growing into the supermassive black holes we see later. The Penn State study published in June 2024 captured the magnitude of the discovery in a single quote. The findings upend conventional thinking about the origins and evolution of galaxies and their supermassive black holes. That's not hyperbole. It's an accurate description of what the little red dots are doing to the field. Conventional thinking assumed galaxies assembled slowly and black holes grew slowly inside them over billions of years. The little red dots show that black holes were already massive and actively feeding when galaxies were still small and still assembling. That's not a minor adjustment to the standard model. It's a complete rethinking of the timeline and the sequence of events. Black holes first, galaxies following. Or at the very least, black holes and galaxies growing together from the start, with the black holes dominating in the early stages before the galaxies caught up. Either way, the old picture is broken. The little red dots broke it. The controversy hasn't settled yet. There's still major disagreement over whether the red light from these objects is dominated by black hole emission, dusty starbursts, or something more exotic. Some researchers argue that the broad emission lines are clear evidence of black holes and that the masses derived from those lines are reliable. Others argue that the masses are uncertain and that the redness could be explained by dust without requiring massive black holes at all. A few have even floated the idea that some of the little red dots might be hosting population 3 stars, the first generation of stars predicted by theory but never observed, or quasi-stars, hypothetical objects where a black hole sits inside an envelope of gas and the whole system shines like a single massive star. Those ideas are exotic, they're not widely accepted, but the fact that they're being discussed at all tells you how uncertain the field still is. The data are good. Webb's observations are sharp and deep and detailed, but the interpretation is still contested because the objects themselves are unlike anything astronomers have seen before. New objects require new models, and new models take time to develop and test. The future of the field is being written right now. More Webb observations are planned, deeper surveys targeting more fields, longer exposures to push the detection limits even deeper, follow-up spectroscopy for individual little red dots to study their properties in detail. The goal is to build up a large enough sample that the statistics become clear. How many little red dots are there? What fraction are dominated by black holes versus star formation? How do their properties change with redshift? Do the black holes at higher redshift, earlier epochs, look different from the ones at slightly lower redshift? Answering those questions requires more data, and more data require more telescope time. Webb's schedule is packed. Every astronomer in the world wants time on the telescope, but the little red dots have become a priority. They're one of the most important discoveries Webb has made, and understanding them is critical to understanding how the universe evolved. Next-generation telescopes are already being planned with the little red dots in mind. The extremely large telescope, under construction in Chile, will have a mirror more than 30 meters across and will be able to take spectra of distant galaxies with much higher resolution than Webb. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will survey large areas of the sky in the infrared, providing a wider view that complements Webb's deep but narrow fields. And further in the future, concepts like the Habitable Worlds Observatory or a next-generation infrared space telescope could push even deeper, detecting objects at redshifts Webb can't reach and studying the little red dots in wavelengths Webb can't access. The field is moving fast. The data are piling up, and the story is still being written. One of the most surprising findings is that the little red dots may be more naturally hosted in low-mass halos and low-mass galaxies than in the massive systems originally assumed. Early models predicted that supermassive black holes would form in the most massive dark matter halos, the deepest gravitational wells where gas could accumulate most efficiently. The little red dots are showing up in smaller systems, less massive galaxies with less extreme environments. That's unexpected. It suggests the conditions for forming massive black hole seeds were more common than anyone thought, and that the process didn't require rare, ultra-dense regions. It could happen in normal environments, typical environments, everywhere. That makes the little red dots even more important, because it means their existence is telling us something fundamental about how structure formed in the early universe, not just in special cases but across the board. The impact of the discovery extends beyond black hole physics. The little red dots are forcing astronomers to rethink how baryonic matter was distributed in the early universe, how reionization proceeded, how the first galaxies assembled, and how black holes and galaxies co-evolved. Every one of those topics is central to cosmology. Every one has been studied for decades using models that assumed black holes grew slowly and didn't dominate until much later in cosmic history. The little red dots are saying those assumptions were wrong. Black holes were important early. They were common early, and they shaped the evolution of the universe in ways the old models didn't account for. That's not a small correction. It's a paradigm shift, the kind that ripples through an entire field and changes how every subsequent observation gets interpreted. There's a quote from the CERN Courier summary that captures the current state of the field. There has been some recent speculation that the little red dots may be marking the end stages of black hole seed growth. That's one interpretation. The idea is that the little red dots are catching black holes right at the moment when they've finished growing from their initial seeds and are about to transition into the more luminous, less obscured quasars we see at slightly later epochs. If that's true, the little red dots are a snapshot of a critical phase in black hole evolution. A phase that only lasts a few tens or hundreds of millions of years, but is crucial for understanding how the seeds turned into giants. Before Webb, that phase was invisible. Now it's not, and studying it in detail is one of the highest priorities in observational cosmology. The little red dots are also raising questions that don't have answers yet. Why are they so compact? Why are they so numerous? Why do some of them show signs of old stars when the universe itself was barely old enough for those stars to exist? Why do the black hole masses vary so widely from object to object? And what determines whether a given little red dot will grow into a ton 618 scale monster or settle into a more modest, supermassive black hole like the one at the center of the Milky Way? Those questions are driving the next generation of research. The answers will require more observations, better models, and probably a few more surprises along the way. Because if there's one thing the little red dots have taught the field, it's that the early universe was weirder and more active than anyone expected. And weird is interesting. Weird is where discoveries happen. The profound impact of these objects on our understanding of the universe's origin and evolution is still unfolding. Every new paper adds another piece to the puzzle. Every new spectrum changes the picture slightly. The field is in the middle of a major transition, the kind that happens maybe once or twice in a generation. The little red dots are not just a discovery, they're a revolution. They're forcing astronomers to go back to the drawing board and rethink the first billion years of cosmic history. And in doing so, they're revealing a universe that was more complex, more violent, and more interesting than the clean linear story we've been telling for decades. There's something humbling about the realization that we've been looking at the early universe for years with Hubble and ground-based telescopes and missing an entire population of objects. They were always there, we just couldn't see them. Hubble's cameras weren't sensitive enough at the right wavelengths. The objects were too red, too faint, too buried under dust. It took Webb's infrared vision to bring them into focus, and the moment Webb did, the story changed. That's the power of better instruments. They don't just show you more of what you already know. They show you things you didn't know were there, things that force you to rewrite the rules. The little red dots are that kind of discovery, the kind that doesn't fit into the old framework, the kind that makes you build a new one. Looking ahead, the next few years are going to be critical. Webb is still observing. More deep fields are planned, more spectroscopy is coming, and as the sample size grows, the statistical properties of the little red dots will become clearer. Are they a distinct population or a phase that every galaxy goes through? Do they exist at all redshifts or only in a narrow window of cosmic time? Do they cluster together or are they randomly distributed across the sky? Those questions will be answered. And when they are, the full story of how black holes and galaxies grew together in the early universe will finally come into focus. The little red dots are the key. They're the missing piece. And now that we've found them, the rest of the puzzle is starting to fall into place. The ultimate question is what this discovery means for the broader narrative of cosmic evolution. The universe started with a big bang. It cooled, hydrogen formed, gravity pulled that hydrogen into clumps, stars ignited, galaxies assembled, black holes grew. That story hasn't changed, but the details have. The sequence has shifted. The timeline has been compressed, and the role of black holes has been elevated from passive passengers to active drivers. The little red dots are showing us that black holes weren't an afterthought in the early universe. They were there from the beginning, shaping the environment around them, feeding on gas, emitting radiation, ionizing the intergalactic medium, and influencing how galaxies formed. They were architects, not tenants. And that changes everything. The discovery of the little red dots is one of those moments in science where the data arrive faster than the theory can keep up. The objects are there. Webb has seen them. The spectra have confirmed their properties. But the models are still catching up. Theorists are scrambling to build simulations that can reproduce the observed population. How do you form thousands of massive black holes in the first billion years after the Big Bang? How do you feed them fast enough to grow them to millions of solar masses? How do you keep them buried under dust while they're feeding? And why are there so many of them? The simulations are getting better, the models are getting more sophisticated, but they're not there yet. The little red dots are still ahead of the theory. And that's a good thing. It means the discovery is real. It means the universe is more interesting than our models predicted. And it means there's still work to do. The little red dots have opened a door, not a window, a door. A wide open door into the early universe that lets us see things we've never seen before. Buried black holes, massive seeds, rapid growth, obscured accretion. All of it happening in the first billion years after the Big Bang, an era that used to be almost entirely invisible to telescopes. Webb has made that era visible, and what we're seeing is forcing us to rewrite the story. Not because the old story was completely wrong. It wasn't, but because it was incomplete. It missed the black holes. It missed the obscured phase. It missed the fact that the universe was assembling its most extreme objects much earlier and much faster than anyone realized. The little red dots are the proof. They're the evidence that the early universe was busy, chaotic, and full of activity we didn't know about until now. The field is only just beginning to grapple with the full implications. The data are still coming in. The models are still being refined. And the debate over what the little red dots actually are, whether they're black hole dominated or starburst dominated or something in between, is still ongoing. But one thing is clear, these objects matter. They're not a minor detail in the story of cosmic evolution. They're a central piece. They're the seeds of the supermassive black holes we see today. They're the hidden phase of black hole growth that was invisible until Webb turned on. And they're the key to understanding how the universe transitioned from a dark, neutral, gas-filled state to the bright, ionized, galaxy-filled cosmos we see around us. The little red dots are rewriting the cosmic story, and the story they're writing is stranger, richer, and more fascinating than the one we thought we knew. We built telescopes to see the universe. We pointed them at the dark, stared for hours, days, weeks, and pulled back photographs of galaxies scattered across time like seeds thrown into an infinite field. We counted them, we measured their distances. We catalogued their shapes and colors and arranged them into neat timelines that told a story we thought we understood. And then we built a better telescope, and the story changed. The little red dots were always there, buried under layers of gas and dust, glowing faintly in wavelengths our eyes can't see, sitting at distances so extreme that their light has been traveling toward us since the universe was an infant. We missed them. For decades we missed them, not because we weren't looking, but because we were looking in the wrong color. Hubble stared at the early universe and saw small, faint, scattered galaxies assembling slowly over hundreds of millions of years. Webb stared at the same sky and saw monsters, compact, red, feeding, already massive when the cosmos was barely 500 million years old. Thousands of them, everywhere. That discovery didn't just add a footnote to the textbook, it ripped out entire chapters. Black holes were supposed to grow slowly. They were supposed to start small and spend billions of years climbing towards supermassive status. The little red dots are telling us they didn't. They started big, or they grew impossibly fast, or both. And they weren't rare anomalies tucked into a few special corners of the early universe. They were common, a standard feature of the cosmic landscape. Which means every assumption we made about how galaxies formed, how black holes grew, and how the two shaped each other over time has to be reconsidered, not adjusted, reconsidered. The paradigm didn't crack, it shattered. And what's left in the rubble is a messier, stranger, more violent picture of the early universe than we ever predicted. A place where black holes formed early, fed aggressively, and dominated their surroundings before galaxies even had time to fully assemble. A place where the seeds of the monsters we see today, the ultramassive black holes weighing tens of billions of solar masses, were already planted within the first billion years. Not as distant future possibilities, as present realities. And here's the part that keeps coming back. The little